56 million years ago, Earth recorded a chemical scream, an impossible carbon spike burned into stone. It looks like the exhaust of industry, the kind that should not exist before humans, and yet it's there. If a civilization once filled the sky with smoke and the seas with waste, would time erase every city and machine, leaving only one horrified geological whisper? Imagine a world that built, burned, and expanded, then slipped beneath geology's grinding silence, not by magic, but by the ordinary violence of time, pressure, and water. After the shock fades, the real unease begins, because the past is not simply buried, it is processed. Mountains rise, basins fill, coastlines migrate, and the seafloor itself is manufactured and destroyed. What survives is rarely a monument. It is a measurement, a ratio, a faint imbalance repeated across the planet. This documentary follows a disturbing possibility, and an even more disturbing alternative, that our methods for reading deep time may be incomplete. If a technological species existed long before us, its cities would not need to endure for the planet to remember it. But if no such species ever lived, then nature alone can still produce signals that feel uncomfortably familiar. Either way, the record forces the same question. What counts as evidence when Earth edits its own history? We will step into the laboratories where ancient oceans are sampled like crime scenes, and where a split cylinder of mud can decide an argument. Under cold storage and clean light, technicians shave millimeters from deep-sea cores, chasing microscopic shells, soot-like residues and trace metals. Instruments translate those fragments into numbers, and the numbers become a story no one can fully control. In that story, carbon is not just an element, it is a signature, and sometimes a warning. Yet signatures can be forged by the planet itself. Volcanoes can flood the atmosphere, intruding magma can cook buried organics, and warming seas can destabilize methane locked in sediments. Rivers can erase a coastline in a century, and glaciers can grind a city into unrecognizable dust. Even biology, given enough time, can remix what we thought was permanent, smearing a sharp moment into a long, deceptive blur. The deeper we look, the more we confront a brutal rule. Absence of artifacts is not absence of events. That is why the search shifts from objects to patterns, global fingerprints that appear in many places at once. We will track isotopes that tilt when light carbon floods the system, and oxygen ratios that shift when the planet heats or cools. We will examine how the nitrogen cycle records disturbance, how lead and mercury can hint at unusual sources, and how black carbon and chemical byproducts can survive where stone cannot. And we will ask, with disciplined skepticism, which combinations could ever point to industry rather than catastrophe? Along the way, we meet a concept that changes the entire case, the Silurian hypothesis. It does not claim an ancient civilization. It asks whether we could detect one if it existed. It treats Earth's archive as a biased medium, preserving the broad strokes while shredding the local details. It also forces a confrontation with equifinality, the uncomfortable truth that very different causes can leave similar traces. In deep time, the world does not label its evidence. From that foundation, we move outward into younger layers where the record grows sharper and the arguments grow louder. There are boundaries in sediment that look like scars, climate shifts that seem to snap into place, and human structures that appear earlier than expected. Each case offers more data, more controversy, and more temptation to reach for a single grand explanation. We will resist that temptation and instead follow what the evidence can actually carry. Because this is not only a story about what might have happened long ago, it is a story about what we're doing now and what will remain when our own buildings are gone. The planet does not keep diaries, it keeps ledgers, and it balances them slowly. When future scientists drill into the strata that include our century, they will not find our names, only our chemistry, and they will argue, as we are arguing, about what it means. So we begin with a simple, unsettling premise. Earth can forget almost everything, yet still remember enough to haunt you. Somewhere between destruction and preservation, between signal and interpretation, a narrow trail of clues survives. Follow it carefully, and you may discover that the most frightening possibility is not an ancient civilization at all. It is the realization that the planet can produce an industrial-looking shadow without any industry, until one finally arrives to make the shadow real. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will move from a forensic deep-sea core to the mechanisms that erase civilizations, then into climate spikes, disputed boundaries, and monuments that complicate official timelines. And at every stop we will test the same idea, whether Earth preserves truth, or only the shapes truth leaves behind. A cylinder of mud and stone rises from the drill rig, sealed and labelled like evidence. Under floodlights, the core glistens with seawater sheen, bands of grey clay, pale carbonate, and darker organic streaks stacked like pages. In a dark lab, technicians split the core lengthwise and read time in millimetres. One half becomes an archive, wrapped and stored cold, while the other half is sampled with careful, almost surgical precision. In the next room, air handlers whisper, and the floor vibrates with pumps. A carousel of vials waits beside a gas chromatograph, and an isotope ratio mass spectrometer warms up like an instrument before a concert. Inside, molecules are ionized, accelerated, and bent through magnetic fields so their masses separate cleanly. The numbers arrive without drama, line after line, then one sequence makes people stop talking. Something was here before us. Not a skeleton, not a tool, not a ruin under jungle vines. It is a pattern in chemistry, locked into rock that formed 56 million years ago. The pattern looks uncomfortably familiar to scientists who study modern industry, sharp, global, and tied to heat. It resembles the kind of planetary signal a civilization can imprint without leaving a single intact artifact. This story begins with a rule that feels like a warning. Earth keeps records, but it does not keep souvenirs. It preserves some traces with ruthless consistency, and it destroys others with equal patience. If you want to ask whether anyone came before us, you have to learn what the planet can remember. Geologists call the most reliable traces fingerprints, not footprints, because deep time rewards repetition. A footprint needs a surface and a moment that survives, undisturbed for ages. A fingerprint can be smeared across oceans, ice, soils, and shells, then pressed into stone. It is not a single object you can hold in your hand. It is a statistical signature that repeats across the world, even when the local details are messy. The most famous fingerprint in this chapter is carbon, the element that ties climate to life. Carbon moves through air, water, life and rock like currency through an economy. Plants pull carbon dioxide from the air, plankton builds shells in the sea, and microbes return carbon to the water column. Over long spans, tectonics and weathering shift carbon between the atmosphere and the lithosphere, balancing the budget slowly. The planet keeps an accounting ledger of that movement in isotopes. Some carbon atoms are lighter, some are heavier, and life prefers the lighter kind. That preference is not philosophy, it is physics. Lighter isotopes react slightly faster, so biology skews the ratio. When the balance shifts fast, the ledger shows it, even if every organism involved is long extinct. Scientists track that balance with a measurement called delta 13C, written D13C. It compares heavy carbon to light carbon in a sample, then compares that ratio to a standard reference. The result is reported in parts per thousand, small numbers that carry large stories. You do not need the math to feel the implication. A sudden drop in D13C means a surge of light carbon entered the system. That light carbon can come from living biomass, from methane, from certain volcanic processes, and from burning ancient organic matter. Methane is especially light, and it can push D13C downward with startling efficiency. Modern fossil fuel emissions carry that same light signature because coal, oil and gas began as buried life. When we burn them, we release carbon that spent millions of years outside the active cycle. When we burn coal and oil, we push D13C downward in the atmosphere and oceans. We are writing our own line into the ledger, and instruments can watch it happen in real time. The ocean absorbs much of that carbon, and as it dissolves it shifts seawater chemistry toward acidity. Even without a catastrophe, the bookkeeping changes, and the rock record will eventually inherit that shift. Now imagine seeing a similar line in rock that predates humans by tens of millions of years. Imagine it is sharp, global, and paired with rapid warming. Imagine it appears in deep-sea mud, in coastal sediments, and in the shells of tiny organisms that once drifted under ancient skies. That is the unsettling premise that opens this documentary. A chemical pattern appears, and for a moment it resembles industrial output. The event has a name that sounds clinical, almost safe. It is the Paleocene-Eocene Thermal Maximum, the PTM. It happened about 56 million years ago, when mammals were small and the poles held forests. The planet warmed quickly, oceans acidified, and ecosystems reorganized under stress. In the sediment record, it looks like a hinge in Earth's climate history. The PEM is not a rumour in one outcrop. It is a coherent signal in marine sediments, in fossil shells, in soil carbonates, and in deep-sea cores. It shows a dramatic negative carbon isotope excursion, a steep Dr13C drop that lasts thousands of years. It also shows a rapid temperature spike, inferred from oxygen isotopes and other proxies. Those proxies are indirect, but they are tested, cross-checked, and repeated. Oxygen isotopes, for example, shift with temperature because evaporation and condensation fractionate heavy and light oxygen differently. When shells form in warmer water, their oxygen isotope ratios change in predictable ways. Other indicators, like the distribution of certain organic molecules, also track heat in ancient seas. None of these tools is perfect alone, but together they build a consistent picture of sudden warming. The scale is what makes it a central puzzle. Something injected a vast amount of carbon into the atmosphere and ocean system, enough to move global isotope ratios. The injection was fast by geological standards. Then the recovery took a long time. The Earth system absorbed the shock, but it did not shrug it off. The carbon cycle had to work overtime, and it took millennia to settle. Scientists debate the source because each explanation has costs. Methane hydrates could release light carbon, but the trigger must be strong and sustained, and the reservoirs must be large enough. Volcanism could add carbon, especially during episodes of massive lava outpouring, but matching the isotope pattern and speed is difficult. Burning of peat and organic soils could contribute, but it raises questions about ignition and extent across continents. There are also hybrid possibilities, where one mechanism starts the process and others amplify it. Warming can destabilize methane, methane can warm further, and feedbacks can cascade across oceans and land. In climate science, feedbacks are not decorations on a theory, they are often the engine. The PEM looks like an engine that ran hot, then slowly cooled. The PEM matters today because it is a natural experiment in rapid warming. It is also a mirror that makes our own emissions look less unique, at least in their chemical direction. When researchers compare rates, modern carbon release may be faster than the PEM, even if total amounts differ. That comparison turns ancient stone into a warning about the present, because rate is what stresses ecosystems. But this documentary asks a different question, one that scientists usually avoid in public. If an industrial civilization existed before humans, could it produce a PTM-like signature? Could it leave a chemical fingerprint without leaving a single surviving artifact? Or does the PTM reveal a blind spot in how we interpret deep time? To ask that question responsibly, we need another rule. Deep time is both incredibly informative and brutally incomplete, and those two truths coexist. 56 million years is not just a long time. It is enough time for continents to move, oceans to open and close, and mountain ranges to rise and collapse. It is also enough time for the record to be edited, sometimes beyond recognition. Plate tectonics is the first eraser, and it works like a conveyor belt with teeth. Ocean crust is created at ridges and destroyed at subduction zones, where it sinks and melts into the mantle. Most seafloor older than 200 million years is gone, not buried, but recycled. If a civilization built coastal cities, ports, and seabed infrastructure, the most likely place to bury it is also the most likely place to destroy it. Erosion is the second eraser, slow and relentless, and it begins the moment something is exposed. Rivers grind mountains into sediment, then spread it across deltas and shelves in broad, shifting fans. Wind strips surfaces, glaciers scrape bedrock, and coastlines migrate with sea level. A skyscraper is impressive for a century, but it is fragile against a million years of weather. Metamorphism is the third eraser, deeper and hotter, and it changes identity rather than location. Burial changes minerals, pressure rearranges crystals, and heat resets chemical clocks. Even if an artifact survives burial, it may be crushed, melted, or transformed beyond recognition. The rock remains, but the object becomes a ghost inside it. Then there is ocean recycling of chemistry itself, a quieter kind of erasure that still matters. Carbonates dissolve and reprecipitate, Pore waters move ions through sediment like slow blood through tissue, and microbes rewrite local signals. Some layers are bioturbated, churned by worms and small creatures until boundaries blur. The geological record is not a perfect archive. It is a palimpsest, rewritten by processes that do not care about our questions. This is why the absence of artifacts proves nothing. Silence in the rock does not mean no one spoke. It can mean the microphone was destroyed, or the tape was recorded over, or the sound never reached the archive. The planet does not preserve evidence evenly, and it does not preserve it for our convenience. Yet the planet does preserve some things with stubborn fidelity, especially when the signal is global. Global chemical shifts can be recorded in many places at once, across different environments and rock types. If a perturbation is large enough, it shows up in multiple independent proxies. That redundancy is why scientists trust the PEPM as a real event, even while arguing about its cause. So what would an industrial civilization leave behind if it existed deep in time? Not a museum of intact machines, not a layer of readable text, not a neat horizon of recognizable debris. The most plausible survivors would be chemistry and stratigraphy, because those are what Earth copies widely. That is the key idea behind a paper that startled the public in 2018. The paper is known as the Silurian hypothesis. The title is a nod to fiction, but the argument is serious and constrained, written in the language of limits. It asks whether a prior industrial civilization, not necessarily human, could be detectable in the geological record. It does not claim such a civilization existed, and it does not smuggle certainty through the back door. Its core answer is sobering. Artifacts are unlikely to survive over tens of millions of years, especially on active continents and ocean basins. Even durable materials would be scattered, buried and altered, then mixed into sediments that later harden into anonymous rock. A civilization could rise, industrialize, and vanish, leaving almost nothing you could point to as a tool. The paper proposes what might survive instead, and the list is familiar because it is already used in modern environmental science. A spike in greenhouse gases and a corresponding isotope excursion, recorded in carbonates and organic matter. Unusual sedimentation patterns from land use and erosion, where soils move faster than nature alone would predict. Elevated concentrations of certain metals from mining and smelting, especially if they appear in strange ratios. It also considers synthetic compounds, if stable enough, or their breakdown products, if distinctive enough to persist. Many modern molecules do not last, but some byproducts can bind to sediments or enter long-lived reservoirs. Even plastics, which feel permanent in a human lifetime, can fragment and oxidize into forms that future geologists might struggle to interpret. The question is not whether traces exist, but whether they are unambiguous. The hypothesis notes a trap in our expectations. We imagine evidence as objects because we are surrounded by objects, and because museums train our intuition. But deep time favors signals that are global, redundant and chemical, the kind that can survive copying. The more a civilization changes planetary cycles, the more it risks becoming detectable, even if every building is erased. This is where the conversation goes quiet in real labs, because the PETM already looks like a planetary scale perturbation. It already has a carbon isotope excursion and rapid warming. It already forces scientists to explain a massive carbon release without a single obvious smoking gun. When a pattern resembles our own footprint, the mind naturally asks why. That does not mean the PETM was caused by industry. Most researchers favor natural mechanisms, and they have strong reasons grounded in geology, volcanism, and feedback physics. But the Silurian hypothesis makes a new kind of question legitimate. It asks whether our methods would even recognize a prior industrial episode as something artificial. The hypothesis also reframes what counts as evidence, and it does so with a scientist restraint. A civilization does not need to leave a statue to be real. It only needs to change the atmosphere, oceans, or sediments in a way that survives. If it did, the signature might look like a climate anomaly, not a ruin. There is another uncomfortable implication, and it cuts in two directions. If the evidence cannot survive, then silence does not mean safety, and it does not mean innocence. The geological record can hide catastrophes, experiments, and mistakes, simply because the archive is selective. It can also hide the fact that something once reached a technological threshold, then disappeared without a trace we would recognize. That tension is the engine of this documentary. We are not hunting for Atlantis in the wrong ocean. We are asking how to read the planet's ledger without projecting our fantasies onto it. We are asking whether deep time contains blind spots large enough to swallow a civilization. If it does, what else might be misfiled as merely natural? To move forward, we need to define the fingerprint more carefully. We need to understand what D13C excursions mean, how warming is inferred, and what sediment and chemical markers can and cannot say. We need to separate a dramatic pattern from a dramatic story because the pattern is real either way. We also need to ask what industrial would mean in a rock record that averages years into layers. We also need to accept a disciplined uncertainty, the kind that keeps curiosity from turning into a claim. The Silurian hypothesis is an intellectual key, not a conclusion. It opens the door to a possibility while keeping the burden of proof intact. It invites scientists to ask better questions about detectability, not to declare an ancient industry as fact. In the chapters ahead, we will follow the carbon spike like a trail through stone. We will examine how the petum is measured, how its timing is constrained, and how its carbon source is modelled. We will test which fingerprints are uniquely industrial and which can be made by nature. We will watch how small ratios and tiny shells become evidence, and how uncertainty is handled rather than hidden. Because the story begins not with ruins, but with a spike in carbon. It is the planet's memory of something that should not be there, or something we do not yet understand. And once you learn how that memory is written, layer by layer, ratio by ratio, you start to wonder what else the stone has been trying to tell us. The petum signal lands like an accusation, but geology answers with a warning. Earth records change, yet it destroys most objects that cause it. In the rocks, the planet keeps ledgers, not diaries, and the pages are constantly rewritten by heat, water, and time. Chapter 1 gave us the fingerprint, not the footprint, and that distinction matters more than it first appears. Chapter 2 explains why footprints almost never survive deep time, especially when they were made on a surface that refuses to sit still. The Silurian hypothesis begins as a detectability problem, not a claim, and its first move is to ask what kind of evidence can even remain. Start with the simplest constraint. The surface of Earth is a thin, active skin. Civilizations build on that skin, and the skin is constantly recycled, cracked, folded, and chemically weathered. From orbit it looks stable, but up close it behaves like a living membrane, always moving, always healing, always shedding. Ocean crust is the fastest eraser, because it has an expiration date measured in geologic moments. New seafloor forms at mid-ocean ridges, where basalt rises, cools, and locks in the chemistry of the seawater above it. Then it moves outward like a conveyor, carrying any sediment blanket with it, as if on a slow belt toward destruction. At subduction zones, it dives, heats, dehydrates, and disappears into the mantle, taking its history down with it. Water bound in minerals is squeezed out, melting points drop, and parts of the slab are transformed into new magmas that return later as volcanoes. What goes down does not come back as a readable archive. It comes back as remixed rock. That matters because coasts are where civilizations concentrate, and they do so for reasons older than our species. Ports, deltas, shelves, and shallow seas collect infrastructure and waste because they are flat, fertile, and connected. Those same margins are also where sediments slide, plates collide, and crust is consumed. So the places we prefer are the places geology prefers to erase. Most ocean floor older than about 200 million years is gone, and that number is not an estimate so much as a limit. The average age of seafloor is young because the entire system is designed to recycle it, and the deep ocean is where time is shortest. If an earlier industry relied on maritime trade, seabed mining, or coastal megacities, the likeliest burial place is also the likeliest destruction route. Picture a continental shelf at night, lit by the imagined glow of a coastal city, and then picture the same shelf 10 million years later. Sea level has shifted, currents have rearranged the sand, and the shelf edge has slumped in a submarine landslide. The city is not a ruin by then. It is a smear of grains, carried downslope into darkness. Continents feel safer, but they are not archives, and their stability is a kind of illusion. Erosion strips relief into grains and ions, then spreads them into basins where they are compacted, altered, and eventually uplifted again. Over millions of years, landscapes are planned down and rebuilt elsewhere, like a sculpture repeatedly ground back into raw material. Rivers are relentless editors of history, and they do their work with patient violence. They cut channels, abandon them, and reoccupy new paths as climates shift and slopes change. Floodplains bury and rework sediments repeatedly, turning any surface layer into mixed material that no longer remembers what it covered. A river delta is especially deceptive because it looks like a place that accumulates, and it does, but it also churns. Channels avulse, switching course in a single season, and the old channel fills with new mud that can be re-eroded later. If a city sat on that delta, its foundations would be undercut, buried, and re-exposed in cycles that shred coherence. Glaciations add a harsher kind of editing, and they do not negotiate with complexity. Ice sheets grind bedrock into flour, bulldoze soils, and erase topography with a moving wall of pressure. They do not preserve cities. They pulverize them and redistribute the fragments across moraines and outwash plains. The visual is stark, a white front advancing, creaking, dragging boulders like teeth. Underneath, the ground is scraped clean, and anything built there becomes a brief ingredient in till. When the ice retreats, meltwater sorts the debris by size, and the story is scattered into gravel bars and silt fans. Coastlines migrate with sea level and tectonics, and they do so far more than human intuition expects. A city on a shoreline is a temporary feature in a shifting boundary zone where waves, storms and tides constantly renegotiate the edge. Storm, subsidence and transgression can bury it, then expose it, then destroy it, and the sequence can repeat more than once. Sea level itself is not a single dial, and the rock record remembers that complexity. Thermal expansion, ice volume and basin geometry all matter, so the shoreline can move even without dramatic climate shifts. Add tectonic uplift or subsidence, and the same coast can be drowned, raised and drowned again, each time reworking whatever lies in its path. Burial does not guarantee preservation, it often guarantees transformation, and that is the part that surprises non-geologists. As sediments compact, pore waters move and minerals recrystallize, filling voids and dissolving edges. Heat and pressure erase original textures and reset chemical clocks, so the very act of saving something can change it beyond recognition. Diagenesis is the quiet middle stage between fresh sediment and rock, and it is relentless. Clays reorganize, organic matter matures, and carbonates dissolve and reprecipitate as cement. A distinct layer can become a vague band, and a crisp boundary can become a gradient that looks like it took longer than it did. Metamorphism is not rare in deep time, even if it feels like an extreme case. Rocks are buried, heated, folded and exhumed during mountain building, and entire regions can be cooked and squeezed. Any artifact caught in that cycle becomes unrecognizable, even if some atoms remain, because the structure that made it meaningful is destroyed. Think of a steel beam entering a subduction-related metamorphic belt, and imagine what survives. Iron oxidizes, then reorders into new minerals, and carbon is driven off or redistributed. The beam does not become a fossil of a beam, it becomes a set of minerals that look completely natural. Even in quiet basins, biology edits the record, and it does so at scales that matter for interpretation. Bioturbation churns sediments as organisms burrow, feed, and ventilate, mixing layers that would otherwise be distinct. A sharp boundary can be smeared into a thicker, ambiguous interval, and that ambiguity can persist for tens of millions of years. The camera would linger on a cross-section of mud, riddled with tiny tunnels, each one a signature of life rearranging the archive. Worms, crustaceans, and microbes do not care about stratigraphic neatness. They turn a clean line into a mottled zone, and they do it everywhere the seafloor has oxygen. Chemical diffusion continues the smearing, even when the sediment looks still. Ions move through pore waters, carbonates dissolve and reprecipitate, and redox fronts migrate as oxygen is consumed and replenished. The signal that survives is often the one that is widespread, because local sharpness is the first thing to be lost. A redox front is a moving boundary between chemical worlds, and it can slide up and down through a core. Iron changes valence, sulfur forms sulfides, and trace metals bind or release depending on conditions. If an industrial pulse left a chemical anomaly, diffusion can blur its edges until it resembles a slower event. This is deep time data loss. The geological record is not missing because nothing happened. It is missing because the storage medium is unstable. The planet is not a museum with glass cases, it is a factory that recycles its own inventory. Now quantify the odds, because intuition fails here, and human timescales mislead. Fossilization is rare even for bones, shells, and wood, and those are materials evolution has already optimized for persistence. For buildings, roads, and machines, the odds are worse because their shapes and compositions are not designed to survive chemistry. Most structures are geologically thin films, and that phrase is not metaphorical. A city is meters thick at most, spread over a few kilometers, perched on a surface that can be stripped in a single erosional episode. In stratigraphy that becomes a blink, easily removed by one unconformity that wipes away time. A road cut is a good visual lesson because it shows how little thickness the surface really has. A meter of soil, a few meters of sediment, then older rock appears, and the present vanishes. If a civilization layer were only a few meters thick, it would be vulnerable to every later incision. A skyscraper feels permanent, but it is a temporary pile of processed minerals assembled against the grain of geology. Concrete cracks as water enters and freezes, steel oxidizes as oxygen finds pathways, and glass devitrifies as its structure relaxes. Given enough time, the materials revert towards sediments, and the sharp geometry dissolves into rubble. Even the most durable alloys are not immune to time when time is measured in millions of years. Corrosion products expand, fracture surrounding material and accelerate decay, while microbes exploit chemical gradients in surprising ways. The end state is not a recognizable machine, it is a dispersed mineral assemblage. Even if fragments survive, they are diluted, and dilution is a form of disappearance. Erosion spreads debris across wide basins, mixing it with natural grains in ratios that overwhelm the unusual. A distinctive object becomes a trace component in a vast sediment budget, and the more time passes, the more the mixing approaches uniformity. Sediment budgets are enormous, and that scale is part of the erasure. A single large river can deliver hundreds of millions of tons of sediment per year, and over 1 million years that becomes a mountain of material. Against that background, a city's worth of debris can be geochemically significant yet physically invisible. Preservation requires a narrow sequence of luck, and each step is a filter that removes most candidates. Rapid burial must occur before scavenging and weathering, and the deposit must avoid later erosion, avoid metamorphism, and avoid subduction. It must also avoid being bioturbated into ambiguity, which is a quieter but common failure mode. That sequence happens, but not often, and the rarity is measurable in the sites we celebrate. It is why paleontology celebrates a Lagerstätte, a rare site of exceptional preservation where conditions align just right. An entire industrial layer would need exceptional preservation on a global scale, which is the opposite of how preservation usually works. Even famous Lagerstätten are local miracles, not planetary norms. They often require anoxia, rapid burial, fine-grained sediment and low disturbance, and even then the record is selective. If we demand intact artifacts as proof, we are demanding the rarest outcome as the standard. So the Silurian hypothesis shifts the target, and it does so with methodological discipline. It asks what a civilization would leave that is not an object, because objects are fragile and local. It looks for signatures that are global, redundant, and chemical, because chemistry can be copied across the planet. Think like a geochemist, not an archaeologist, and the world changes shape. A civilization is an energy system that moves elements, and it does so faster than natural background rates. If it is large enough, it perturbs cycles that the planet already tracks, and those perturbations can be recorded as anomalies. Carbon is the first and loudest candidate, because carbon is the currency of climate. Industrial activity tends to mobilize ancient carbon quickly, pulling it from coal, oil, gas, or other reservoirs that took eons to store. Rapid carbon release pushes D13C negative, because buried organic carbon is isotopically light compared to the atmosphere and ocean. That isotopic language needs a plain translation, because the symbol can hide the idea. D13C is the ratio of heavy carbon to light carbon compared to a standard, and living systems prefer the lighter isotope. When a lot of ancient organic carbon is burned or released, the whole ocean atmosphere system shifts toward lighter values. Oxygen isotopes add the temperature context, and they do it through the physics of fractionation. Warming shifts D18O in carbonates and biogenic minerals, because the isotopic balance between water and mineral depends on temperature. Combined D13C and D18O changes can indicate carbon injection paired with heat, which is the pattern that catches attention. The visual here is a split screen of two curves, both bending sharply at the same horizon. One curve tells you about carbon sources, the other about temperature and ice, and together they act like a lie detector. When both move fast, the planet is telling you something happened quickly. Nitrogen offers another ledger, because it sits at the intersection of biology and combustion. Fertilizer production, combustion, and land conversion can shift nitrogen isotopes and the balance of nitrate and ammonium. Over time, those shifts can be recorded in sediments and organic matter, especially where productivity and burial are high. On Earth, nitrogen is often the limiting nutrient, so changing it changes ecosystems. If a civilization fixes atmospheric nitrogen at industrial scale, it can amplify blooms, alter oxygen demand, and reshape food webs. The rock record might not show factories, but it can show a sudden sustained push in the nitrogen cycle. Then come trace metals, the quiet fingerprints of extraction, and they matter because they are usually locked away. Mining and smelting mobilize elements that are typically concentrated in ore bodies rather than spread evenly. Lead, mercury, copper, zinc, and others can spike in unusual patterns, and those patterns can persist as geochemical scars. Trace metals also have isotopes, and isotopes can carry provenance like an accent. Lead isotopes, for example, vary with the age and type of crustal source, so a sudden global shift might imply widespread processing of particular ores. The challenge is that nature also moves these metals, sometimes in dramatic pulses. Mercury is especially useful because it travels globally, riding the atmosphere before settling into oceans and soils. Volcanism also emits mercury, so interpretation is hard and scientists have to compare timing and co-occurring proxies. But ratios, speciation, and association with organic matter can still constrain sources even when the signal is noisy. A mercury spike in a core can look like a thin dark line, almost casual, until you realize it represents a planetary scale redistribution. The narrator's voice slows here, because the implication is unsettling. Something, somewhere, pushed mercury into the sky, and the sky delivered it everywhere. Lead can mark industrial processing, but it also has natural pathways that complicate the story. Weathering, hydrothermal systems, and volcanism move lead too, and dust can carry it across continents. The question becomes whether the distribution is anomalous in space and time, and whether it aligns with other industrial-like indicators. Black carbon and soot offer a combustion layer, and they are visually evocative in cores. Large-scale burning produces char, soot, and polycyclic aromatic hydrocarbons, and some forms can persist and be measured long after the flames are gone. These residues can settle into lakes and oceans, forming a darkened interval that whispers of fire. But soot is not uniquely industrial, and that is the trap the hypothesis refuses to ignore. Wildfires and volcanic events can create similar residues, and even lightning can ignite vast burns under the right climate. A spike in black carbon is evidence of burning, not evidence of factories, unless other lines of evidence converge. Sedimentation changes can also betray land use, because land use changes the hydraulics of erosion. Deforestation and agriculture increase erosion rates and change grain sizes delivered to oceans, often increasing fine sediment loads and organic flux. In cores, that can appear as abrupt shifts in clay, silt, and accumulation rates, like a landscape suddenly losing its skin. Yet nature can do that too, and it does, repeatedly, without any help from intelligence. Climate shifts alter rainfall and vegetation, and tectonics changes drainage by lifting mountains or tilting basins. A sediment pulse can be human, or it can be monsoon reorganization, and the core alone may not tell you which. This is where the hypothesis becomes uncomfortable and rigorous, because it refuses easy conclusions. It forces a distinction between detectability and attribution, and that distinction is the scientific heart of the chapter. Detectability asks whether a signal could survive. Attribution asks whether a signal has a unique cause. In other words, can we see it? And if we can see it, can we name it? Many things leave marks, but few marks come with signatures that point to only one culprit. Deep Time is a courtroom with missing witnesses and damaged evidence. Now introduce synthetic markers, because they feel like the obvious proof, and because modern intuition clings to them. Plastics, fluorinated compounds, industrial solvents, and novel polymers seem like future fossils, the kind of thing that should shout across time. The problem is that deep time is chemically aggressive, and even stubborn molecules face heat, pressure, and radiation. Plastics fragment quickly in sunlight and oxygen, and that is only the beginning of their transformation. They become microplastics, then nanoplastics, then oxidized residues that can be metabolized or incorporated into other organic matter. Over millions of years, many polymers will depolymerize, crosslink, or be consumed by microbes that evolve to exploit new carbon sources. The visual shifts to a plastic bottle dissolving into a cloud of particles, then into a faint chemical haze in sediment. The object disappears, but the chemistry lingers, and that lingering is the real question. What survives is not the shape, but the altered distribution of elements. Some plastics may leave indirect traces, and indirect traces are often more durable than the thing itself. Additives, pigments, and stabilizers contain metals and halogens, and those elements can bind to clays or organic matter after breakdown. Their breakdown products could leave a chemical halo, a subtle enrichment that is easier to measure than to interpret. PFAS-like molecules are more persistent in modern environments, and their persistence is famous for a reason. Their carbon-fluorine bonds resist many degradation pathways, so they can survive where other compounds fail. But over tens of millions of years, heat, radiation, and metamorphism can still destroy them, and burial can expose them to temperatures that rewrite chemistry. Even if fragments persist, distinguishability is not guaranteed, and that is another deep time lesson. Ancient organic matter is complex and can mimic synthetic fragments, especially after diagenesis rearranges functional groups. Diagenesis can produce molecules that resemble industrial byproducts, and a false positive is always waiting. So the best synthetic hope may be not a recognizable polymer, and that is a sobering pivot. It may be an unusual distribution of halogens, isotopic anomalies in industrial feedstocks, or rare compounds trapped in exceptional settings. The evidence might be statistical rather than iconic, more like a forensic profile than a photograph. Exceptional settings exist, but they are rare, and rarity is the recurring theme of preservation. Anoxic basins can preserve organic molecules better than oxygenated shells, because oxygen drives decay and mixing. Rapid burial in fine sediments can protect fragile compounds from oxidation, and low bioturbation can keep boundaries sharper. Imagine a stagnant basin with a dark, laminated seafloor where no worms churn the mud. Each year lays down a thin sheet, like pages in a book, and the pages stay separate. If anything can preserve a chemical whisper, it is a place like that, sealed from disturbance. Still, the hypothesis does not depend on plastic surviving like artifacts, and it does not need a polymer fossil to make its point. It depends on the idea that industry becomes a geological event, and geological events are recorded as system-wide shifts. A short pulse can leave a long shadow in the cycles, because feedbacks amplify and recovery takes time. Define that event in Earth system terms, and the narrative becomes more precise. Rapid CO2 rise drives warming, which intensifies the hydrologic cycle and changes how water moves through the atmosphere. Warmer oceans expand and stratify, reducing oxygen at depth as mixing weakens and respiration consumes what remains. Acidification follows as CO2 dissolves into seawater, forming carbonic acid and shifting carbonate chemistry. Carbonate shells dissolve more easily, and calcifying organisms are stressed, especially in surface waters where they build reefs and tests. In sediments, carbonate content can drop sharply during acidification intervals, leaving clay-rich horizons where limestone should be. Anoxia leaves a distinct sedimentary signature, and it is one of the clearest system responses to rapid warming. Low oxygen favours preservation of organic matter and changes metal chemistry, because many elements behave differently without oxygen. Elements like molybdenum and uranium can enrich under anoxic conditions, and iron can form sulfides that darken the rock. The camera would show a black shale layer, glossy and ominous, sandwiched between lighter sediments. That darkness is not just colour, it is chemistry. And chemistry is memory. It tells you oxygen was scarce, life was stressed, and decay slowed enough for carbon to accumulate. Biotic turnover follows environmental stress, and the fossil record registers it as a reorganization of communities. Species ranges shift, communities reorganize, and extinctions cluster, especially among specialists. In microfossils, assemblages change rapidly, and recovery can take long intervals, because ecosystems rebuild slowly after rapid shocks. These are the kinds of changes the PETM already shows, and that is why it keeps returning to the centre of the story. It has warming, acidification signals, and ecological disruption, recorded in multiple basins and multiple proxies. That resemblance is why the Silurian hypothesis points directly at it, like a detective circling a familiar pattern. But resemblance is not identity, and scientists know the trap, because geology is full of lookalikes. Earth has many ways to push carbon and heat quickly, and several of them require no intelligence at all. The record can show the same pattern from different causes, and the rock does not label its triggers. This is equifinality, a core problem in interpreting proxies, and it is more than a technical term. Different processes can converge on similar outcomes in the rock record, producing the same curve with different stories behind it. A negative D13C excursion can come from methane, volcanism, or burning biomass, and each pathway has its own physics. A warming spike can come from CO2, methane, or ocean circulation changes that trap heat in different layers. Anoxia can come from warming, nutrient influx, or basin restriction that limits ventilation. A metal spike can come from volcanism or erosion of ore-rich terrains, and the core may not reveal which without additional context. Equifinality is why extraordinary claims are avoided, not because scientists lack imagination, but because the archive is ambiguous. If multiple natural mechanisms can explain a signal, the burden shifts to unique markers that narrow the possibilities. Scientists demand specificity because deep time is generous with patterns and stingy with labels. So what would count as uniquely industrial in deep time, if we are honest about ambiguity? A combination of signals that align in timing and mechanism, and that appear globally rather than locally. A rapid, global carbon isotope excursion paired with unusual metal ratios and synthetic residues would be harder to dismiss, because it would require multiple coincidences. Even then, uncertainty remains because the record is incomplete, and incompleteness is not a minor caveat. We sample scattered outcrops and sparse cores, then interpolate globally, and the interpolation can hide regional complexity. Time resolution blurs events that were sharp in reality, and sharpness is often the clue. Dating adds another layer of caution, because sediments do not deposit like clockwork. Sediments accumulate at different rates, and hiatuses remove time without leaving obvious scars, especially in marine settings. A 1,000-year pulse can be stretched into a thicker layer, or erased entirely at one site, and both outcomes are common. This is why the hypothesis is framed as a question, and why that framing is not rhetorical. Could we detect a prior industrial episode given what survives, given the filters of erosion, metamorphism, and mixing? The answer is yes in principle, but only through indirect fingerprints, and only if those fingerprints are strong enough. Now build the tension without crossing into assertion, because the tone must stay disciplined. The hypothesis does not prove a pre-human civilization existed, and it does not need to be valuable. It proves that no artifacts is not evidence of no civilization, because the planet is skilled at erasing artifacts. It also reframes our own future, and that reframing is the mirror held up to the viewer. If we vanished, our cities would not become a neat fossil layer, stacked like a textbook diagram. They would become a brief geochemical disturbance, plus scattered materials that are hard to interpret, mixed into the ordinary sediments of rivers and seas. Future scientists might find our era as a boundary, not a ruin, and that boundary would be defined by chemistry. They might argue about causes the way we argue about the PEP, because they would inherit the same ambiguity. They would see a carbon spike, warming and biotic stress, then debate the trigger, and the debate would be shaped by what survived. That is the mirror the Silurian hypothesis holds up, and it is why it feels unsettling rather than playful. It is less about ancient aliens and more about how Earth archives disruption, then hides the disruptor. It asks whether we are overconfident in what absence means, and whether we confuse silence with innocence. Return to the central question to keep the documentary anchored, because the narrative must not drift. Do PETM and anomalies indicate a pre-human industrial civilization, or do they reveal a blind spot in how we interpret deep time? If the archive is biased toward chemistry, then chemistry becomes the witness we must cross-examine. The scientific posture is careful, but the implication is sharp, and it cuts in two directions. If chemistry is the only surviving witness, then we have to interrogate chemistry like testimony, weighing context and consistency. We have to ask what it can say, and what it cannot, and we have to accept that uncertainty is part of the answer. So we narrow the search to the most coherent confession in the Cenozoic, the one already famous for its abruptness. A global carbon isotope crash, a rapid temperature jump, and a recovery that took millennia, recorded across oceans and continents. The PETM is the case file, thick with proxies and arguments. Next, we examine that case file line by line, because the details are where attribution lives. We test the carbon sources, the rates, and the feedbacks, and we compare them to what we know about industrial perturbations. We ask whether any signature in the PETM is uniquely industrial or only disturbingly familiar, because the story still begins not with ruins, but with a spike in carbon, and that spike is the kind of thing rocks remember. And in deep time, a spike can be the only thing that survives, standing in for everything else that was lost. If chemistry is the only surviving witness, then we interrogate the biggest chemical confession in the Cenozoic. The Paleocene, Eocene thermal maximum, sits at about 56 million years ago, a boundary time that arrives like a slammed door in the stratigraphic record. It is not a local anomaly or a single outcrop story, and it does not belong to one ocean basin. It is a global stratigraphic event, repeated across oceans and continents, and it is legible in cores pulled from abyssal plains. In the lab, that legibility becomes a line on a graph, but in the rock it is a sudden change in colour, texture, and chemistry. Picture the world it strikes, because background climate sets the stage for every shock. The Paleocene is already warm, with no permanent polar ice sheets, and sea level stands high enough to drown broad continental shelves. Forests reach into high latitudes, and the poles are not deserts of ice but damp, seasonal landscapes with long summer light. The ocean is stratified differently than today, and circulation patterns respond to a planet with smaller temperature gradients. Against that background, the PETM is not merely warm, it is a sudden acceleration of warmth, a spike that makes an already hot planet lurch. Define it cleanly before the mystery grows teeth, because the event has a technical definition as well as a narrative one. In a geologically short interval, global temperatures rise roughly 5 to 8 degrees Celsius, and some regions likely experience even higher peaks. The oceans acidify as carbon floods the atmosphere and dissolves into seawater, altering carbonate chemistry from the surface down to the deep. That shift changes pH and carbonate ion availability, which is plain language for how easy it is to build shells. Ecosystems reorganize under heat, acidity, and shifting rainfall, and the map of habitable zones redraws itself. In the sediment record, the PETM is a sharp hinge. Before and after look like different climate regimes. The PETM matters because it is both well documented and still not fully explained, which is a rare and unsettling combination. It is the scientific core of this documentary, because it is measurable in multiple independent archives, including marine microfossils and terrestrial soils. It is also the core because it refuses to close under modelling, even after decades of refinement and better computers. The event is old, but the argument about it is modern, and the stakes feel uncomfortably current. When an ancient perturbation resembles a present-day trajectory, even loosely, it becomes harder to treat it as a curiosity. Start with the fingerprint that makes the PETM unmistakable, because without it the event would blur into ordinary climate noise. It is the carbon isotope excursion, often shortened to CIE, and it appears like a sudden tilt in the planet's carbon ledger. In many records, D13C drops abruptly and stays low for thousands of years, then slowly climbs back. That drop is seen in deep-sea carbonates, in organic matter, and in soils, which means it is not a single environment trick. The signal is coherent enough that sites can be correlated globally, like matching a scar across different bodies. In the field, that correlation is a kind of time machine. One thin layer becomes the same moment, everywhere. Explain D13C without hiding behind symbols, because the symbol is shorthand for a physical preference. Carbon has isotopes, mainly 12C and 13C, which behave almost the same chemically but not quite the same physically. D13C reports the ratio of 13C to 12C compared to a standard, expressed in parts per thousand, and the sign tells a story. Biology prefers the lighter 12C because it diffuses and reacts slightly faster, so living and once living carbon tends to be 13C depleted. That fractionation happens in photosynthesis, in microbial metabolism, and even in some carbonate precipitation pathways. When D13C swings negative across the whole system, It implies a large addition of light carbon, injected faster than the system can hide it. The key is mass balance, not just direction, because the carbon cycle is a set of connected reservoirs with different sizes. A small carbon release can move local D13C, especially in restricted basins or soils, but it cannot tilt the entire ocean atmosphere reservoir by itself. The PEM excursion is large enough to demand a massive carbon injection, and the math is unforgiving once you choose reasonable reservoir sizes. The exact amount depends on assumptions about pre-event carbon inventories, mixing rates, and how much carbon entered as methane versus CO2. Even conservative estimates imply thousands of gigatons of carbon, and many reconstructions push higher when they try to match the full suite of evidence. The uncomfortable implication is that Earth can mobilize carbon on a scale that rivals the biggest human numbers, even without humans. Then show how the measurement is anchored in real material, because the proxy is not abstract. Foraminifera build carbonate shells that record seawater chemistry, and those shells rain down through the water column like microscopic snow. Over time, they accumulate on the seafloor and become part of sediment layers, pressed into a quiet archive. Scientists sample individual species to reduce ecological bias, because different forams live at different depths and seasons. They also screen shells for recrystallization, because diagenesis can rewrite the signal after burial. They measure D13C in the carbonate and in associated organic carbon, then compare patterns across sites to separate global change from local noise. The CIE is not the only line of evidence, and it cannot stand alone, because isotopes tell you carbon moved but not exactly how hot it got. Temperature proxies also shift sharply at the PEM boundary, and they do so in ways that reinforce the carbon story rather than contradict it. Oxygen isotopes in carbonates move in the direction expected for warming, because warmer water changes the fractionation recorded in shells. Organic proxies, including lipid-based thermometers, also point to rapid heat, especially in surface waters where biology responds quickly. Some records show tropical seas pushing toward physiological limits, where oxygen solubility drops and heat stress rises together. Multiple tools agree on a big temperature jump, even when they disagree on exact magnitude. Now lock the PETM into time, because timing is where the tension lives, and where hypotheses either survive or collapse. The onset appears rapid in many sections, possibly a few thousand years or less, which is a blink in stratigraphy. Some records suggest an even sharper initial step, though resolution limits complicate certainty, and sediment mixing can smear the first moments. Ash layers, orbital tuning, and sedimentation rate estimates provide clocks, but each clock has error bars that matter. Recovery is slower and stretched, on the order of hundreds of thousands of years, and it refuses to snap back. The curve looks like a punch and a long bruise, and the bruise is the part that lingers in every model. This pattern is familiar in Earth system physics, and the familiarity is not comforting. Abrupt forcing can shift climate quickly when thresholds are crossed, especially in systems with reinforcing feedbacks. Long recovery can reflect slow negative feedbacks like silicate weathering and carbonate compensation, which operate on timescales that dwarf human lifetimes. Weathering is slow chemistry made fast only by time, turning CO2 into bicarbonate that rivers carry to the sea. The PEM has the shape of a fast injection followed by slow cleanup, and that shape is part of what makes it feel modern. It also raises a quiet question. How many other spikes were erased by time, leaving only the ones big enough to survive? But the PEM is not just a temperature curve and an isotope line, because life is also a sensor. It is a biological event recorded in extinctions, migrations, and community turnover, as if the biosphere is forced to resort its own inventory. In the deep sea, benthic foraminifera suffer a major extinction, and the loss is concentrated among species adapted to stable, cold, oxygen-rich bottom waters. That pattern hints at warming, oxygen stress, and food web disruption reaching even the seafloor. On land, mammal communities reorganize and some lineages show dwarfing, a pattern often linked to heat stress and altered food quality. Plants shift ranges as rainfall patterns change, and pollen records hint at regional drying and wetting that do not move in simple unison. Ocean chemistry leaves its own scars, and those scars are spatial, layered by depth like a bruise that spreads. Acidification reduces carbonate saturation, especially in deep waters where pressure is high and temperatures are low. Carbonate dissolution horizons shoal, and carbonate content drops in many deep-sea cores, sometimes abruptly enough to form a distinct clay-rich interval. Clay-rich layers appear where carbonate would normally dominate, and the colour and texture change can be visible even before the lab work begins. Under the microscope, the damage is literal: etched shells, fragmented tests, and missing carbonate that should have been there. The seafloor becomes a chemical battleground, and the archive records both the attack and the defence. These dissolution patterns are not decoration, they are constraints, because seawater chemistry has rules that cannot be negotiated. Any explanation has to match the timing of acidification and the depth pattern of carbonate loss, because chemistry obeys gradients. It must also match how quickly the ocean's buffering capacity was overwhelmed, which depends on how fast carbon entered and where it entered. It must explain why some basins show stronger dissolution than others, and why some sites preserve carbonate where neighbours lose it. The PETM is global, but it is not uniform, and that unevenness is a clue rather than a nuisance. Now the documentary's central question presses in, because the signature is provocative. Do these anomalies indicate a pre-human industrial civilization, or do they reveal a blind spot in how we interpret deep time? The PETM is the test case because it looks like a system-wide carbon shock, complete with an isotopic fingerprint. It also looks like something models should be able to reproduce because the boundary is clear and the proxies are abundant. When the best tools still struggle, imagination creeps into the gap, sometimes responsibly, sometimes not. The responsible move is to ask what the rocks can and cannot distinguish. Scientists have spent decades building carbon cycle and climate models for the PET, and the effort has the feel of a long interrogation. They tune ocean mixing, weathering feedbacks, carbonate chemistry and carbon sources, then ask the model to confess in numbers. They compare outputs to D13C curves, temperature proxies, and dissolution horizons, and they test whether the same parameter set can satisfy all of them. They try to satisfy all constraints at once, because a single match can be accidental. Again and again, something fails to fit cleanly, and the failure is often where the science becomes most informative. In Earth science, the mismatch is not an embarrassment. It is a map pointing to missing physics. The first unresolved piece is the carbon source, because isotopes are picky witnesses, and they do not accept vague answers. A negative D13C excursion demands 13C depleted carbon, but not all sources are depleted enough to do the job efficiently. Methane is extremely light, and can drive big D13C shifts with less total carbon, which makes it attractive in mass balance terms. Organic carbon from soils and peat is also light, though less extreme, and it comes with plausible pathways for mobilization. Volcanic CO2 is heavier and struggles to produce the full excursion alone, unless the amounts are enormous or the carbon is mixed with something lighter. Candidate 1 is methane hydrates, the ice-like methane deposits in marine sediments, stable under cold temperatures and high pressures. They contain very 13C depleted carbon, so they match the isotope direction with striking efficiency. Warming oceans could destabilize hydrates and release methane, and methane oxidizes to CO2, driving further warming and acidification. The problem is reservoir size and trigger plausibility at required scales, because the hydrate inventory must be both large and vulnerable. Another complication is that hydrate stability depends on seafloor temperature gradients, which vary by basin and depth. Even a small warming at the wrong depth can move the stability boundary like a sliding trapdoor. Hydrate release also faces a rate problem, and rate is where the story becomes mechanically demanding. Hydrates can release quickly in local failures, like submarine landslides or focused venting, but global release at PTM scale is harder to sustain. The ocean would also oxidize much methane before it reached the atmosphere, converting it to CO2 while consuming oxygen and altering local chemistry. That oxidation changes water column redox conditions, which can ripple into nutrient cycling and productivity. Models can make hydrates work, but often only with strong assumptions about rapid, widespread destabilization and efficient atmospheric transfer. The mechanism remains possible but not settled, and it continues to provoke debate because it resembles a natural version of a runaway. Candidate 2 is volcanism tied to the North Atlantic igneous province, a vast magmatic episode associated with rifting as the North Atlantic opens. Around the PETM, rifting and magmatism intensify, and the crust is fractured by intrusions and eruptive centers. Volcanoes emit CO2, and they can warm climate over long intervals, especially when eruptions and degassing persist. Volcanism also emits sulfur and mercury, leaving potential geochemical markers that can be searched for in sediments. The challenge is isotopic composition. and matching the abruptness. Because steady volcanic degassing does not naturally produce a sudden isotopic cliff. A slow leak can change climate, but it does not easily explain a sharp isotopic step. Volcanic CO2 is not light enough to explain the full D13C drop by itself, and that mismatch is stubborn. To get the excursion, models often require either enormous CO2 amounts or additional light carbon sources, which turns volcanism into a partial answer. Volcanism can be a trigger rather than the whole story, warming the system until other reservoirs tip. That hybrid framing is common in the literature because it respects both the tectonic context and the isotope constraint. It also fits a broader pattern in Earth history. Big climate events often involve a trigger and an amplifier. Candidate 3 is thermogenic methane from magma intruding into organic-rich sediments, which is a more chemically targeted version of the volcanic story. When sills bake carbon-rich layers, they can generate methane and CO2 that are isotopically light, because the source material is ancient organic carbon. This mechanism links directly to the same North Atlantic magmatism, but it shifts attention from lava to subsurface plumbing. It can also produce rapid pulses if gas escapes through fractures and vents, creating short-lived surges rather than a smooth ramp. The uncertainty is how much gas was produced and how fast it escaped, because both depend on the geometry of intrusions and the permeability of surrounding rocks. In some reconstructions, the seafloor becomes a vent field, with carbon escaping through pathways that are now only hinted at in seismic images. Candidate 4 is oxidation of peat, soils, and biomass on land, a pathway that turns climate change into its own fuel. A warmer climate can dry regions, increase wildfire, and expose stored carbon, especially in wetlands and peatlands that accumulate organic matter under waterlogged conditions. Oxidation releases CO2 with a light isotopic signature, and widespread burning can leave charcoal and altered organic markers. This pathway can be large if carbon stores were extensive in Paleocene landscapes, which some reconstructions suggest. It still needs a trigger and a way to scale globally, because regional drought does not automatically become a planet-wide carbon release. The land surface is patchy, and patchiness is the enemy of simple accounting. Candidate 5 is permafrost-like carbon release, even in a warmer world, because warm does not mean uniform. High-latitude soils can store carbon, and warming can mobilize it through microbial decomposition, erosion, and hydrologic change. The Paleocene had forests near the poles, but soil carbon reservoirs could still exist in seasonally cold or waterlogged environments. Release could amplify initial warming and deepen the D13C excursion, especially if it occurred in bursts tied to hydrological shifts. The difficulty is quantifying a reservoir so far back in time when the landscapes themselves are inferred rather than observed. The proxy record can suggest carbon moved, yet it rarely tells you exactly where it was stored. None of these candidates is fringe science, and none is a complete solution on its own, which is precisely why the PETM remains open. The PETM likely involved multiple sources and feedbacks, braided together in a way that is hard to unweave. One process can initiate warming, another can amplify it, and ocean chemistry can prolong recovery by controlling how carbon is stored. That is a reasonable Earth system story, and it is consistent with how complex systems behave under stress. It still leaves stubborn mismatches, and those mismatches are where the documentary keeps its tension. If the system needed a cascade, then the hard question becomes which domino fell first. The second unresolved piece is the injection rate, because the planet reacts differently to a drip than to a blast. Some sections imply a very fast onset, perhaps in a few thousand years, and the sharpness is visible even in cores with modest resolution. Others suggest a stepped onset, with an initial spike and then sustained input, as if the system stuttered before committing. Bioturbation and sedimentation rates blur sharp events, so apparent speed is hard to interpret, and different depositional settings smear differently. Even the chemistry can be mixed downward by burrowing organisms, turning a sharp boundary into a gradient. Yet many researchers agree the onset was fast by geological standards, fast enough to outpace several buffering processes. Rate matters because rate controls stress, and stress controls biological outcomes. A slow carbon release can be buffered by ocean chemistry and weathering, allowing carbonate systems time to adjust and organisms time to migrate. A fast release overwhelms buffering and drives stronger acidification, especially in deep waters where renewal is slow. Rate also affects how much warming is needed to trigger feedbacks like hydrate destabilization, because threshold behavior depends on how quickly conditions change. The PTM's rate remains one of the hardest parameters to pin down, and it is one of the most consequential. It is the difference between a world that adapts and a world that breaks. The third unresolved piece is spatial patterning, which is where a global event becomes a geographic puzzle. The PETM is recorded globally, but the magnitude varies by location and proxy, and those variations are not random. Some regions show stronger warming, others show stronger dissolution, and some show both, suggesting different combinations of circulation and chemistry. Ocean circulation changes can redistribute heat and carbon, altering where acidification hits hardest and where oxygen declines. Stratification can trap carbon in surface layers, while deep waters lag behind, creating time offsets that look like contradictions. Any model must match not just averages but geography, because the ocean is not a bathtub, and the atmosphere is not perfectly mixed on short timescales. Now explain why decades of modelling struggle to close the case, because the difficulty is structural rather than a lack of effort. Models must satisfy mass balance, isotope mass balance, and the ocean chemistry simultaneously, which means every adjustment echoes through multiple constraints. They must reproduce the size and shape of the D13C excursion in multiple reservoirs, including surface ocean, deep ocean, and terrestrial carbon. They must match carbonate dissolution horizons and recovery timescales, which are controlled by alkalinity and sediment interactions. They must also fit temperature proxies without overdriving the system, because too much warming breaks biological and geochemical consistency. The PETM is a multi-lock door, and each key turns a different bolt. A model can match the isotope excursion by adding very light carbon, but that choice has consequences. It can match warming by adding enough greenhouse forcing, yet the implied CO2 levels must remain plausible given proxy constraints. It can match dissolution by pushing ocean saturation low enough, but then it must recover in a way that matches sediment records. When it matches one constraint, it can break another, and the break is often subtle at first. Too much methane can overshoot warming or require implausible oxidation pathways, while too much volcanic CO2 can miss the isotope shift and smear the onset. The model can be right in shape and wrong in mechanism, which is a dangerous kind of agreement. The recovery tail is another constraint that refuses to be ignored, because it encodes the planet's cleanup mechanisms. The system returns toward baseline over roughly 100,000 to 200,000 years, which is too long for simple atmospheric mixing and too short for tectonic rearrangement. That timescale points to slow negative feedbacks like silicate weathering and carbonate burial, processes that remove CO2 by turning it into rock. Models can reproduce a long tail, but the exact shape varies with assumptions about runoff, temperature dependence, and ocean alkalinity. The tail also implies the carbon was not instantly removed, which rules out some simplistic scenarios. A fast pulse can start the event, but a long tail says the system stayed loaded. Carbonate compensation adds complexity, and it does so in a way that can hide evidence while creating it. As the ocean acidifies, seafloor carbonates dissolve, increasing alkalinity and buffering the system, which is a chemical counterpunch. That buffering can shorten the most extreme acidification, but it also changes sediment records by removing carbonate that would otherwise be measured. Dissolution can erase parts of the signal, especially in deep basins, and the missing carbonate becomes part of the story. The archive is both witness and victim, and that dual role makes interpretation delicate. When the witness is damaged, the interrogation becomes harder, even if the crime is obvious. This is where the documentary's tone turns darker, because the PTM is a warning mirror for today, regardless of cause. It shows that Earth can warm dramatically with a large carbon pulse, even when starting from a warm baseline. It shows that oceans acidify and ecosystems reorganize under that stress, and that the reorganization is not gentle. It shows that recovery is slow, even when the trigger is brief, because the planet's long-term thermostat is made of rock chemistry. It also shows that deep ocean ecosystems can be hit hardest, even when the forcing begins at the surface. The PETM does not need to be human to be instructive, and it does not need to be unique to be frightening. Now introduce the phrase that makes scientists cautious in public, because it can be misunderstood in a single breath. Some researchers describe an industrial-like fingerprint in the PETM pattern, and they do so with careful qualifiers. They mean rapid carbon addition, negative D13C, warming, acidification, and biotic stress in a tight package, a suite that resembles what we are building now. They do not mean smokestacks in the Eocene, and they do not claim artifacts where none exist. Similarity in signature does not equal identity of cause, and the distinction matters. A fingerprint can tell you the type of event, yet still leave the culprit unknown. Handle that resemblance carefully, because it is where speculation can outrun evidence. Industrial emissions today are 13C depleted because they come from buried organic carbon, and that isotopic lightness is part of the modern fingerprint. Natural methane and organic carbon releases can produce the same isotopic direction, and they can do so rapidly if thresholds are crossed. Rapid injection can occur without intelligence if the system is primed, and the PETM may have been primed by warmth and tectonics. The rock records outcomes, not intentions, and it is silent on motives. In deep time, chemistry is a lie detector, but it is not a biography. Still, the resemblance creates scientific discomfort for a reason, and it is not merely rhetorical. The PETM looks like a system responding to a sudden carbon shock, and the response is coherent across multiple independent proxies. It looks like the kind of perturbation humans are creating now, but on a different baseline world with different coastlines and circulation. It forces scientists to ask how sensitive the climate system is to carbon, especially when feedbacks are engaged. It forces them to ask how feedbacks can amplify an initial push, and whether those amplifiers have hidden thresholds. If the past contains threshold behavior, then the future might as well. The discomfort is also methodological, because it touches the credibility of our tools. If the PETM cannot be fully explained, then our understanding of carbon cycle extremes is incomplete, even if our broad narrative is correct. If our models cannot match all constraints, then projections carry unquantified risk, especially for rapid change scenarios. The PETM becomes a stress test for Earth system theory, not because it is identical to today, but because it is one of the best natural experiments we have. A stress test is only useful when it fails, and the PETM fails in instructive ways. It tells us where our equations are strong and where they are still guessing. Bring the central question back into focus without claiming an answer, because the chapter is about detectability as much as causation. Could a pre-human industrial civilization create a PETM-like carbon signal, at least in principle? In principle, any large-scale combustion of ancient carbon would drive the 13 EC negative, and it would do so in both atmosphere and ocean. In principle, rapid emissions would warm and acidify oceans, leaving dissolution horizons and ecological stress. But the PETM predates humans by tens of millions of years, and there is no direct artifact trail, no mines, no metals, no unmistakable manufactured residue. The absence of artifacts is not a hand wave, it is a boundary condition on what we can responsibly infer. The Silurian hypothesis frames this as detectability, not accusation, and that framing is the only responsible way to hold the idea. The PETM provides a real example of how a global carbon perturbation looks in stone, including the parts that are unambiguous and the parts that are frustratingly ambiguous. It also shows how attribution remains uncertain even with abundant data, because multiple natural pathways can converge on similar outcomes. If something had been here before us, the PETM is the kind of layer we would argue about, and we would argue fiercely. That's the blind spot the hypothesis exposes, and it is a blind spot made of chemistry, not imagination. But the PETM also pushes back against easy narratives of artificiality, and it does so with context. The event aligns broadly with known tectonic and volcanic reorganizations, including rifting and widespread magmatism in the North Atlantic region. It sits in a climate system already warm and ice-free, where feedbacks can behave differently than in an icehouse world. Natural Earth processes are capable of abrupt transitions, especially when reservoirs of carbon are large and stability is conditional. The planet does not need a factory to surprise us, and that realization is its own kind of unease. If nature can generate an industrial-like signature, then the signature alone cannot convict. So the chapter holds two truths at once, and neither is comfortable. The PETM resembles our era in its chemical direction and its ecological stress, and the resemblance is not superficial. The PETM is also plausibly natural, driven by volcanism and carbon feedbacks, which is exactly what Earth has done before. The resemblance is a warning, not a verdict, and it should sharpen caution rather than inflate certainty. The uncertainty is not failure, it is the honest state of the evidence, and honesty is what keeps the science useful. In a story about deep time, humility is not a mood, it is a method. Now tighten the unresolved list, because the audience needs the open wounds clearly labelled. What was the dominant carbon source, and what was the mixture, and did the mixture change during the event? How fast was the onset, and was it stepped or singular, and how much of the apparent shape is sediment smearing? How did ocean circulation and carbonate buffering shape the spatial pattern, and which basins took the hardest chemical hit? Why do some proxies disagree on magnitude and timing, and what does that disagreement reveal about proxy limits? Each question is narrow, but the answers connect, and that connectivity is what makes the case so hard to close. Then state the consequence of not knowing, because uncertainty has a cost. If we cannot close the PETM, we cannot fully bound Earth's response to rapid carbon release, and we cannot be sure we have captured the worst-case feedbacks. We can still learn from it, because its direction is clear and its impacts are real. Carbon in, heat up, oceans acidify, life reorganizes, and the sequence repeats across environments. Recovery takes far longer than the initial shock, and that asymmetry is the lesson that refuses to soften. The past does not promise disaster, but it does document possibility. This is the deep time mirror, and it does not flatter us. It shows that the planet registers carbon shocks in a consistent language, written in isotopes and dissolved carbonate. It also shows that the language can be spoken by nature without any intelligence behind it, which makes the threat feel impersonal. The horror is not that someone did it before us. The horror is that it can happen at all, and that the cleanup is slow even when the cause is fast. When rock becomes the record keeper, time becomes the punishment. End with a forward pull into the next chapter's closer evidence, because distance blurs and proximity sharpens. If the PETM is the deep time mirror, then we look for nearer mirrors, where the stratigraphy is less worn and the clocks are tighter. We look for events close enough to touch, where layers are sharper and dating is tighter, and where the arguments get louder because the evidence is less eroded. We follow the same fingerprint toward younger stone, and we see what changes and what refuses to change. Because the story still begins not with ruins, but with a spike in carbon, and the spike is still speaking, even when we cannot agree on its voice, and even when the witness is only chemistry. Deep time taught us a hard rule. The record keeps fingerprints, then shreds the objects that made them. In the oldest rocks, heat and pressure erase details, leaving only chemistry and broad patterns behind. Minerals recrystallize, pores collapse, and fluids migrate, so a once sharp signal becomes a softened smear. Even when a story is real, the medium that stores it is always changing, trading certainty for inference as the planet keeps working. What survives is often not the event itself, but a chemical afterimage that must be interpreted with restraint. Now we move closer to the present, where layers sharpen and arguments get louder. The late Quaternary is not a rumour in stone. It is ice, mud, pollen, charcoal and glass that can be dated, resampled and fought over. The archives are younger, the clocks are tighter, and the temptation to treat them as photographs grows stronger. Yet even here, the planet speaks in codes, and those codes still demand translation, because every archive has a bias built into its physics. A lake favours what falls into it, an ice sheet favours what snows onto it, and neither preserves the world evenly. The Younger Dryas begins about 12,800 years ago, near the end of the last deglaciation. After warming that looked like a clean exit from the Ice Age, temperatures in the North Atlantic region plunge back toward near-glacial conditions. The shift is abrupt enough to feel like a switch, not a slope, and it lasts roughly 12 centuries. In some reconstructions, the cooling arrives within decades, which is almost instantaneous on geological scales. A world that had been opening, ice retreating, forests advancing, coastlines redrawing, suddenly tightens again, as if the climate system hit a hidden latch. The shock is not just in the magnitude, but in the speed. Because speed is what breaks ecological expectations. Picture the North Atlantic at that moment, not as a map, but as a moving surface. Sea ice spreads farther south, brightening the ocean skin and reflecting sunlight back into space. That extra reflectivity, the albedo effect, is simple in plain language. A whiter planet absorbs less heat. But the feedback is more than brightness, because sea ice also seals the ocean, reducing heat and moisture transfer into the air above it. Storm tracks reorganize, and the winds that deliver moisture to continents shift their aim, changing where snow piles up and where drought settles in. In Europe and parts of North America, Landscapes that had been greening are pushed back toward tundra and steppe. The change is not uniform everywhere, but the signal is strong enough and coherent enough to anchor an entire debate. In the visuals, you can almost watch the boundary, a line where forests hesitate then retreat. The name itself carries history. Younger Dryas comes from Dryas octopetala, a cold-loving alpine flower whose pollen appears in European sediments during this return to chill. Early geologists and botanists read those pollen shifts like a botanical thermometer, long before ice cores made the event famous. In the 19th and early 20th centuries, Scandinavian and European researchers were already mapping these cold pulses in peat and lake mud. That older tradition matters, because it reminds us the boundary was recognized first as a living response, plants moving, ecosystems tightening, before it became a headline in isotope curves. The event entered science as a change in life, not a change in numbers. In Greenland ice cores, the onset reads as a sudden change in chemistry and isotopes. Oxygen isotopes shift in a way that implies rapid cooling, because heavier and lighter oxygen are sorted by temperature and condensation processes. When air masses cool, they preferentially drop out heavier isotopes, leaving the snowfall isotopically lighter. That subtle ratio, measured layer by layer, becomes a thermometer written in frozen water. It is not a direct thermometer though, because it also depends on where the moisture came from and how storms travelled. Even the seasonality of snowfall can matter, because winter-dominated accumulation can bias the annual signal toward colder months. The ice also carries aerosols, acids and dust, each with its own logic. Dust and aerosol markers change, suggesting altered winds and aridity, and the annual layers let scientists count time with unusual precision. Some sections are so clearly banded that they resemble tree rings, winter and summer stacked like pages. Electrical conductivity spikes can hint at acidic inputs, while sodium and chloride can track sea salt aerosols carried inland by stronger winds. Trapped bubbles preserve ancient air, and with it the greenhouse gases of that moment, linking temperature to the atmosphere rather than guessing from temperature alone. In the lab, those bubbles are released and measured with instruments that can detect parts per million, small numbers that carry large implications. Those bubbles add another layer of nuance. Air is sealed in ice only after snow compresses into firn and then into solid ice, so the gas age can lag the ice age. Scientists correct for that offset with densification models and comparisons across cores, because timing is the whole argument here. When the curves line up, temperature proxies, dust and gases, they form a synchronized story that is hard to dismiss. Still, the story is never a single line. It is a set of lines that must be aligned with care. A few decades of misalignment can change whether one process leads and another follows. On continents, pollen records register ecosystems reorganizing as climate whiplashes. Each grain is a tiny capsule of plant identity, carried by wind and water into lakes and bogs. Forest taxa retreat and cold-tolerant plants expand, then reverse again when the younger Dryas ends. In a core, that shift can look like a forest pulling back from the shoreline, then returning, as if the land itself is breathing. But pollen is also a census with distortions. Some trees flood the air with grains, while others whisper their presence. Pine can dominate a record even when it is only part of the landscape, while insect-pollinated plants may barely register at all. Lake sediments show changes in grain size, organic content and valve structure, reflecting shifts in runoff, ice cover, and productivity. Coarser grains can mean stronger meltwater pulses or more energetic streams, while finer silts can imply calmer conditions and stable ice. Organic content can rise with warmer, more productive summers, and fall when growing seasons shorten. In some lakes, valves, annual layers, form a seasonal calendar, with light summer sediments and dark winter deposits alternating like a metronome. Under magnification, those layers can look like a barcode, each band a year that either held together or broke. In a clean sequence, you can count years like steps, and then watch the rhythm change. These are proxies, not photographs, and they have rules. Ice cores preserve atmospheric and precipitation signals in layered snow that becomes ice, but the signal is filtered through storm tracks and source regions. Pollen preserves regional vegetation in a statistical rain of grains, but the rain is biased toward prolific producers like pine and birch. Lake sediments preserve local hydrology and erosion, then lock it into stratigraphy, yet a single flood can rewrite a year. The strength of proxy science is not perfection, but cross-checking. many imperfect witnesses telling a consistent story. When independent archives pivot together, the probability of coincidence shrinks, even if each archive is noisy. Proxies also have limits that matter for controversy. A core can be mixed by burrowing, smeared by diffusion, or interrupted by a hiatus that deletes time. In lakes and wetlands, worms, roots, and small organisms can churn the upper layers, blurring sharp boundaries into thicker bands. Chemical diffusion can soften abrupt changes, especially for mobile ions and gases, and the smoothing can mimic gradual change even when the event was sharp. Dating can be tight in ice and loose in lakes, and correlation across continents can turn a sharp event into a broader band. Even the act of coring can disturb a delicate interface, compressing a thin horizon into something that looks deceptively thick. The boundary can be real and still be hard to sample cleanly. Even with those limits, the Younger Dryas boundary stands out as a thin horizon. It is a moment where multiple archives pivot together, and that coherence is why it attracts extraordinary explanations. The feeling is not just that climate changed, but that it changed with a kind of punctuation. If the PEM was a deep time mirror, this is a nearer mirror with cleaner edges. The question becomes harder to avoid. What can flip a planet's regional climate so quickly and hold it there for centuries? And just as important, what kind of trigger leaves a signature thin enough to hide in millimeters? The mainstream explanation does not require an impact. It centers on ocean circulation, especially the Atlantic meridional overturning circulation, the system that moves heat northward. Warm, salty surface water flows north, releases heat to the atmosphere, grows denser, and sinks to form deep water. That sinking is like a pump, pulling more warm water northward and exporting cold water south at depth. If that conveyor weakens, the North Atlantic cools quickly, sea ice expands, and atmospheric patterns shift. The effect is regional but powerful, because the North Atlantic is a hinge where ocean and air exchange energy fast. In modern observations, we can measure that exchange directly, which makes the ancient mechanism feel less speculative. A trigger for AMOC disruption could be meltwater. As ice sheets retreat, they can dump fresh water into the North Atlantic through pulses, lakes, and rerouted rivers. Fresh water is buoyant, it caps the ocean surface, and it can suppress deep water formation that drives overturning. The physics is straightforward in plain language. If the surface becomes too fresh, it refuses to sink. Without sinking, the conveyor stalls, and the North loses a major source of imported heat. Salinity is not just saltiness here. It is density control, a quiet lever that can move an entire circulation pattern. In a stratified ocean, even a relatively thin freshwater lid can change how the whole column breathes. The late glacial world was primed for these disruptions. The Laurentide ice sheet still covered much of North America, and its meltwater had multiple pathways to the sea. Proglacial lakes could grow enormous behind ice dams, storing fresh water like a loaded spring. When those dams failed, the release could be sudden, and the routing could change as the ice margin shifted. A river that once drained south could be forced east or north, redirecting fresh water into sensitive ocean regions. In that landscape, geography was temporary. Valleys became channels, and channels became dead ends. The map was not a static background. It was part of the mechanism. Internal variability can also produce abrupt transitions when the system has thresholds. Climate is not always a smooth response to smooth forcing. It can jump between states when feedbacks align, especially in an ice age world with large ice sheets and sensitive circulation. Sea ice is a powerful amplifier because it changes albedo and insulates the ocean from the air. Once sea ice expands past a point, it can reinforce cold conditions, and once it retreats, warming can accelerate. The system behaves less like a dimmer switch and more like a set of gears that can catch. The unsettling implication is that small nudges can matter most when the system is already near a tipping point. The Younger Dryas is also part of a broader pattern of abrupt events in glacial records. Greenland ice cores show repeated Dansgaard, Ushga oscillations, rapid warmings and coolings that demonstrate how jumpy the system can be. Those events are not identical to the Younger Dryas, but they show that the climate machine has gears, not just a dial. That history matters because it makes an abrupt Younger Dryas less mysterious in principle. It suggests a world where thresholds are real and where the ocean, ice-atmosphere system can reorganize quickly. If abruptness is a recurring behavior, then the real puzzle becomes timing. Why this switch here and not a century earlier? timing is where mechanisms become testable, because triggers must arrive when the system is ready. But alongside that conventional framework sits a competing claim. Some researchers argue the Younger Dryas began with a cosmic impact or airburst, or a fragmented comet interacting with the atmosphere and ice. They point to a boundary layer, reported at many sites, that appears to contain high-energy markers. The proposal is not merely that something fell from the sky, but that it left a diagnostic signature in sediments at the exact moment the climate turned. It is a claim about coincidence so precise that it dares you to call it accidental. It also invites a visual language of shock waves, thermal flashes, and a sky that briefly becomes a source of danger. The impact hypothesis is not a single data point. It is a bundle of proposed indicators that are said to co-occur near the onset. The bundle includes nanodiamonds, microspherules, melt glass, platinum group element anomalies, and widespread burn signals. The rhetorical force of the bundle is its convergence, many different kinds of evidence, each pointing toward extreme conditions. If they truly align in time and space, the argument becomes hard to ignore. If they do not, the bundle unravels into separate stories that only look unified from a distance. The scientific tension lives in that gap between clustered and synchronous. Nanodiamonds are carbon crystals measured on the nanometer scale. They can form under extreme pressures and temperatures, including impacts that shock carbon-bearing material. When a shockwave passes through carbon-rich sediments or biomass, it can rearrange atoms into diamond structures. They are also reported in some meteorites and impact ejecta, which makes them attractive as a diagnostic marker. In the lab, they are identified through microscopy and spectroscopy, where crystal lattice patterns and characteristic signals separate them from soot and graphite. The difficulty is that diamond at this scale can include different structures, and each structure has its own signature. Even the difference between a true lattice and a lookalike can hinge on how a sample was prepared and how a spectrum was interpreted. Supporters report nanodiamonds at Younger Dryas boundary sites across 4 continents. The claim is that the distribution is too wide for a local fire or volcano, and too consistent to be random contamination. The claim is also that the timing is tight, clustering near the onset rather than spread through the late glacial. In the most dramatic telling, the nanodiamonds are like glitter in the sediment, tiny, stubborn, and difficult to explain without a high-energy event. Yet glitter can also be static, clung, and misleading, and that is why the methods matter as much as the particles. If the crystals are real, they should appear with predictable companions, not as lonely curiosities. Microspherules are another pillar of the case. They are tiny, often iron-rich or silica-rich spheres that can form when material melts and then cools in flight. Surface tension pulls molten droplets into spheres, and rapid cooling freezes them in that shape. High-temperature processes can produce them, including impacts, industrial furnaces, volcanic eruptions, and intense fires. Under a microscope, they can look like miniature planets, sometimes with textured surfaces that hint at rapid quenching. Chemistry becomes the next question. What elements are inside, and what does that recipe imply about the furnace that made them? A spherule with terrestrial ratios tells one story, while one with unusual enrichment suggests another. Melt glass and glassy spherules raise the temperature argument further. Some samples are described as quenched glass formed at temperatures above typical wildfires, implying brief but intense heating. Some are described as containing unusual compositions that imply rapid melting of surface sediments, including mixtures of minerals that do not usually fuse together. In visual terms, it is as if a patch of ground was flash-heated, liquefied, and sprayed into the air. The question is whether nature can do that without an impact, or whether we are underestimating what rare terrestrial fires can accomplish in the right soils. Temperature is not just a number here. It is a constraint on what processes are even possible. Then there are platinum and iridium group anomalies. These elements are rare in Earth's crust and relatively enriched in some extraterrestrial material, which is why they are used as tracers. A spike in platinum at the boundary has been presented as a cleaner signal than iridium, which is famously tied to the KP impact. Platinum can also be measured with high sensitivity, and a sharp excursion can stand out against low background values. The argument is not that platinum proves a comet, but that it is consistent with one, provided the spike is primary and not later mobilized. The analytical precision can be exquisite, but the geological context still decides what the number means. Charcoal peaks and soot-like residues are used to argue for widespread burning. Some records show elevated charcoal or black carbon near the boundary, sometimes paired with other proposed impact markers. The interpretation is a continent-scale fire episode, potentially ignited by an airburst, thermal radiation, or secondary ecological collapse. In a cinematic reconstruction, the sky would brighten, forests would ignite, and smoke would spread across hemispheres. Yet in the real record, charcoal is subtle. Tiny fragments, counted and normalized, then interpreted through context. The same black flecks can mean crown fires, grassland burns, or peat smouldering that never produce towering flames. Fire leaves traces, but it does not label its own cause. The narrative implication is obvious and dangerous. If a cosmic event can flip climate abruptly, then the surface can be reset within a human lifetime. If any human societies existed in that interval, even small and mobile ones, their world could be erased without leaving cities. Shorelines could shift, rivers could reroute, and the best places to live could drown or dry out. The absence of monumental ruins would not be evidence of absence, only evidence of what preservation allows. The question becomes uncomfortable. How many human stories have been edited out by rising seas and moving sediment? And how many of our assumptions are built on what the ocean has already swallowed? But the controversy is not just about drama. It is about replication, methods, and what counts as a robust boundary marker. The quaternary record is rich, but it is also messy, and the difference between signal and artifact can be a single lab step. If the boundary is real, it should survive independent tests, independent labs, and independent sampling strategies. If it fails those tests, then the story becomes one of expectations shaping what we see. Science advances here not by winning an argument, but by narrowing what is still plausible. The most valuable outcome is not a headline, but a constraint that holds. Nanodiamond detection is technically difficult. The particles are tiny, they can be confused with other carbon forms, and extraction protocols can introduce contamination or bias. Different labs use different preparation steps, different microscopes, and different criteria for identification. Acid treatments can concentrate resistant particles, but they can also create residues that resemble the target. Even the choice of filters, containers, and lab air can matter when the objects of interest are measured in nanometers. At that scale, a fingerprint from a glove is not a metaphor. It is a real source of carbon. The method must be as carefully documented as the result, because the method can manufacture the illusion. Some teams report clear nanodiamond signals. Other teams fail to find them at the same sites, or find them in layers outside the boundary. Critics argue that the reported crystals can be misidentified, or that the signal is not unique to the younger Dryas onset. The dispute becomes a question of standards. What counts as a nanodiamond, and what counts as convincing proof? In a field where the particles are smaller than bacteria, certainty is expensive. One lab's diagnostic can be another lab's ambiguous, and the difference may be a threshold setting. The argument is not only about nature, but about measurement. Microspherules face similar problems. Spherules can form in many contexts, including volcanic ash, lightning strikes, and even modern industrial pollution that falls onto sediments. The industrial problem is especially sharp because modern fly ash can travel far and settle quietly into cores. If a site is near human activity, modern contamination can masquerade as ancient signal unless controls are strict. That means clean sampling, careful stratigraphy, and independent confirmation that the spherules are truly ancient. It also means asking an unromantic question: are we measuring the Pleistocene or the last century? A single contaminated horizon can mislead an entire interpretation. Melt glass is also not automatically extraterrestrial. Intense biomass burning, peat fires, and localized high-temperature events can produce glassy material, especially when soils contain silica and salts. Some compositions can be explained by burning of silica-rich soils, though the temperature constraints remain debated. The key question is duration and peak temperature. Wildfires can be hot, but they are rarely hot everywhere at once. An impact, by contrast, can deliver extreme temperatures in a brief pulse, but it must leave other consistent traces too. A single exotic-looking glass fragment is a clue, not a conclusion. The record demands a pattern, not a trophy. Platinum anomalies are intriguing, but they are not a verdict. Platinum can be concentrated by geochemical processes, redeposited by water, or affected by post-depositional mobility. In some environments, metals can move with groundwater, binding to organic matter or iron oxides, then reprecipitating at chemical boundaries. A spike must be shown to be primary, synchronous, and widespread, not a local concentration. The more complex the sedimentary setting, the easier it is for chemistry to imitate catastrophe. A boundary can be a chemical trap as well as a historical marker. The question becomes whether the spike is a signal from the sky or a signal from the sediment. Charcoal peaks can reflect climate-driven fire regimes without any impact. The late glacial was a time of rapid vegetation change, shifting moisture and unstable ecosystems. Fire responds strongly to fuel availability and dryness, and those can change abruptly with circulation shifts. If forests retreat and grasslands expand, fire behavior changes, and charcoal production can rise. The same charcoal peak that looks like ignition from above can also look like drought and wind at ground level. In other words, the climate event itself can manufacture the burn signal that later gets blamed on a trigger. That circularity is exactly why independent markers matter. The scientific dispute often turns on correlation. Does the boundary layer represent one moment, or a time-transgressive set of deposits that appear aligned only because the dating is broad? Are the markers truly synchronous across sites, or are they being aligned by expectation and narrative pressure? When a researcher knows where the boundary should be, the risk of confirmation bias increases, even with good intentions. This is why blind tests and independent replication carry so much weight. The boundary is thin, but the temptation to thicken it with interpretation is always present. A millimeter can become a story, and a story can become a target. It also turns on sampling strategy. Many boundary sites are thin, disturbed, or incomplete, and the boundary can be literally millimeters thick. A centimeter of sediment can represent decades in one lake and centuries in another, and bioturbation can mix that centimeter into a thicker interval. If you sample too coarsely, you smear a sharper vent into a broad hump. If you sample too narrowly, you may miss it entirely because the boundary is not always where you expect. The practical reality is a person with a core, a scalpel, and a decision about where to cut. That decision, made in a quiet lab, can determine whether an impact seems obvious or invisible. So the impact hypothesis lives or dies on redundancy. If multiple independent markers align at the same horizon, across many settings, the case strengthens. If markers appear inconsistently or outside the onset, the case weakens toward coincidence and selection. The most persuasive scenario would be one where chemistry, mineralogy, and stratigraphy all point to the same moment. The least persuasive scenario is one where each site offers a different piece, and the pieces only fit after heavy interpretation. The boundary must behave like a boundary, not like a collage. In practice, that means clean stratigraphy, consistent protocols, and results that survive skeptical retesting. This is the same logic we used in deep time. A single proxy can be fooled, because nature has many ways to mimic a single signal. A convergent suite is harder to dismiss, but it must still be tested against natural alternatives. The burden is not just to show something unusual, but to show that the unusual thing has no plausible terrestrial pathway. In science, extraordinary claims do not require extraordinary belief, but they do require extraordinary constraint. The constraint is the real currency: tight methods, tight stratigraphy, tight timing. Without that discipline, the boundary becomes a mirror that reflects our preferences. The alternative story remains powerful because it is mechanistic and already expected. Meltwater pulses are real, recorded in sea level rise and ice sheet retreat histories, and they have the right timing to matter. Ocean circulation is known to flip states, and abrupt climate events appear repeatedly in glacial records. Models and modern observations both show that freshwater can weaken overturning, and that sea ice can amplify the response. The conventional explanation fits within what we already know the climate system can do. It asks us to accept a complicated system, not a single spectacular blow. Complexity is less cinematic, but it is often more faithful to how Earth behaves. The Younger Dryas ends abruptly too, which supports a circulation threshold view. Temperatures rebound quickly into the early Holocene, and the isotopic curves climb like a sudden release of tension. The system behaves like it has multiple stable modes, and it can jump between them when pushed. That symmetry, fast down, fast up, feels like a switchable circulation regime. It also complicates a simple impact narrative, because an impact can start an event, but it does not easily explain a clean, rapid termination. If a trigger lit the fuse, what snuffed it so neatly? The end looks less like a crater's aftermath and more like a pump restarting. Still, the impact hypothesis persists because it offers a single trigger for a complex package. It also offers a way to connect climate whiplash with ecological shock and extinction, turning a climate event into a catastrophe narrative. That narrative is compelling, and it is easy to overstate because humans are pattern seekers and story makers. Yet the persistence also reflects a real scientific instinct. When multiple anomalies cluster near a boundary, it is rational to ask whether they share a cause. The question is not irrational. The question is whether the record answers it cleanly. If the answer stays fuzzy, the responsible posture is curiosity without surrender. Megafaunal extinctions cluster around this broader transition, though timing varies by species and region. Mammoths, mastodons, giant ground sloths, and other large animals disappear across the Americas, and similar losses occur elsewhere. The causes are debated, involving hunting pressure, habitat change, and rapid climate shifts that stress reproduction and food supply. Large animals are often vulnerable because they reproduce slowly and require extensive ranges. When climates fragment landscapes, the margins of survival can collapse quickly. A shrinking corridor can be as lethal as a spear, especially when winters lengthen and forage becomes patchy. In the background of the boundary, you can imagine quieter scenes. Tracks in snow, thinning herds, and landscapes that no longer provide predictable refuge. The younger Dryas is not the only suspect in those extinctions, but it is part of the stress landscape. Rapid cooling and drying can fragment habitats and reduce forage, especially when plant communities reorganize faster than animals can adapt. Human predation can become more consequential when populations are already weakened and when migration corridors narrow. The debate is not a simple choice between climate and humans, because both pressures can act together. The boundary becomes a stage where multiple forces converge. When we look for a single culprit, we may be misunderstanding how real collapses happen. Collapse is often a stack of pressures that arrive close enough together to feel like one blow. This is where the documentary's central question tightens again. If Earth can pivot this fast, then the absence of durable ruins proves almost nothing. A small coastal or riverine society could be disrupted, displaced, or absorbed, leaving only indirect traces. Sea level was still rising, and many shorelines from that time now lie underwater, beyond casual excavation. Rivers can bury camps under meters of sediment, and wind can erase surface traces in a few seasons. What survives is not what mattered most, but what happened to be stored in the right place. Preservation is a lottery, and the tickets are made of geology, but we must keep the logic clean. The Younger Dryas boundary does not prove a lost civilization, and it does not require one to be interesting. It demonstrates that abrupt climate transitions can occur within a human timescale, and that ecosystems can reorganize quickly under that pressure. It also demonstrates how fragile evidence can be, even when the event is real. The boundary is a warning about both climate and epistemology, about what the planet can do and what the record can hide. If a dramatic story is true, it still has to pass through the narrow gate of preservation. That gate is selective, and it closes without explanation. The boundary also reinforces the motif of layers. The PEM was a thick global chemical confession spread across deep time, blurred by millions of years of sedimentation. The Younger Dryas is a thin horizon, a sharper scar close enough to touch with a coring tube. Earth speaks in layers, and the layers do not explain themselves. They offer clues, and they demand interpretation, and they punish certainty. A thin layer can carry more argument than 1,000 meters of rock, because it concentrates change into a narrow band. In a close-up shot, the boundary can look almost trivial, until you remember what it represents. A boundary layer is a kind of sentence written in sediment. It is short, it is dense, and it can be read in many places, though the handwriting changes with each environment. The argument is over what the sentence means, and whether it names a cause or only a consequence. Is it a record of the trigger, or a record of the system's response? When we read a sentence without its author, we risk projecting our own plot. The more dramatic the plot, the more careful the reading must be. The boundary invites interpretation, and it punishes impatience. So we hold the controversy fairly. There are reported markers that suggest extreme heat and unusual chemistry at the onset, and some of those reports show striking alignments. There are also serious replication disputes, plausible terrestrial mechanisms, and methodological pitfalls that can generate false positives. The scientific process here is not a courtroom drama with one decisive exhibit. It is a slow tightening of constraints, where some signals survive and others fade under scrutiny. Over time, the field does what it always does, separating what is repeatable from what is merely exciting. The result may be less satisfying than a single answer, but it is more trustworthy. Regardless of the trigger, the Younger Dryas boundary raises the stakes of the whole series. The planet can change abruptly without waiting for slow geology, and the consequences can cascade through ecosystems. The surface can be reset while memories still live in human minds, and while stories can still be told around fires. That possibility changes how we think about absence, because absence may be the expected outcome after disruption. If the world can pivot in decades, then culture must be able to pivot too, or break. The boundary is not only a climate event, it is a test of resilience written into the ground. That is the bridge to the human story. If catastrophe can wipe the surface clean, survivors would adapt fast, build differently, and encode the shock into myth and ritual. They would not leave skyscrapers, because the incentives would be wrong and the time would be short. They would leave patterns, alignments, and places that feel out of time, because those are durable ways to store meaning. They would also leave gaps, quiet intervals where the record thins, and later people inherit a world that seems newly made. What would you choose to preserve if you believed the climate itself could turn on you? Would you trust stone, or would you trust memory? We follow the layers forward, from chemistry to climate to culture. The next chapter enters a site that should not exist when it does, at least not in the way it does. Göbekli Tepe waits at the edge of the Younger Dryas aftermath, like an answer that arrived before the question. Its stones stand where we expect simpler traces, and that mismatch forces us to look again at what the late glacial world could produce. The boundary behind it is not just a date, it is a pressure, a context, and a shadow. In the camera's slow approach, carved pillars rise from the earth like a message that survived the reset. If something was here before us, the planet would not preserve its skyline. It would preserve its boundary layers and force later scientists to argue over the thin horizons. In that argument, over dust and diamonds, charcoal and platinum, we hear the deeper theme of this series. The past is not gone, but it is filtered, and the filter is the Earth itself. And when the filter is violent, the surviving record can look like a riddle that dares us to solve it. We leave the thin scar of the Younger Dryas and enter the ground itself, where time is stacked in layers and meanings survive unevenly. We move from global proxies into archaeology, where stone survives longer than stories, and where absence can be as informative as presence. The central question stays the same, even as the evidence changes shape and scale. Do anomalies imply something before us, or do they expose a blind spot in interpretation, an assumption so familiar we stop seeing it? On screen, the scale tightens from planetary curves to a ridgeline, and the camera begins to feel the texture of terrain. Göbekli Tepe sits in southeastern Anatolia, near Şanlıurfa in modern Turkey, where pale limestone rises above wide plains and shallow valleys. The hill is not dramatic like a mountain, yet it commands the landscape, an intentional place to see and be seen. In the early Holocene, these slopes held stands of wild einkorn and other grasses, and herds moved through the mosaic of steppe and woodland. Springs and seasonal drainages would have mattered here, because water is the quiet architect of where people gather. Aerial footage can linger on the ridge's gentle dome, then drift outward to the surrounding basins, showing how a meeting place becomes legible from distance. From ground level, the horizon is broad and open, and the wind has room to speak. The limestone underfoot is bright and brittle in the sun, but it is workable, and that matters for monumentality. This is not a place where stone must be imported from far away, because the hill itself offers the raw material. The site was noticed earlier as a mound, but excavation in the 1990s changed its status from curiosity to turning point. Under the soil were not scattered tools or a simple shrine, but architecture that looked planned, repeated, and monumental. Radiocarbon dates place major activity roughly 9600 to 8000 BCE, a span that straddles the end of the Younger Dryas and the beginning of a warmer, more stable Holocene. Those dates are not guesses from style alone. They come from organic materials associated with construction and use, calibrated against known fluctuations in atmospheric carbon. In practical terms, the method measures how much radioactive carbon remains in once living matter, then corrects for past changes in the carbon cycle. A visual overlay can show a simplified calibration curve, not as math, but as a reminder that the atmosphere itself has a history. The narrator can emphasize that calibration is a humility check, because raw radiocarbon years are not the same as calendar years. Even so, the broad window holds. This is early, and it is securely early. The time frame sits close to the threshold where we stop expecting large formal architecture, and that proximity is part of the shock. The basic facts are not in dispute, even when interpretations are, because the stone is stubborn. The architecture is monumental, built from local limestone quarried and shaped on site, where the bedrock itself becomes both foundation and raw material. Circular and oval enclosures were cut into bedrock and ringed with massive pillars, set into sockets and linked by low stone walls. Many pillars are T-shaped, some reaching several meters tall and weighing many tons. Their surfaces dressed smooth in places and left textured in others. Two larger central pillars often stand in the middle of an enclosure, like paired presences anchoring the space. The layout repeats with variation, suggesting a shared template that could be adapted rather than copied blindly. Visually, the camera glides along the edge of an excavated ring, and the geometry reads as deliberate even in ruin. The pillars rise from the earth like pale silhouettes, their tops catching light while their bases disappear into shadowed fill. Tool marks become visible at close range, pecking, scraping and smoothing that imply time, planning and practiced hands. Even without metal, stone-on-stone work can be precise, and limestone yields to patient percussion and abrasion. The rhythm of labour is visible in the surface, because every strike leaves a tiny decision behind. A close shot can linger on the slight facets where a pillar was dressed, then cut to a reconstruction of stone hammers and flint tools striking limestone. The sound design matters here, because it turns an abstract feat into a physical one. You can almost count the hours in the texture, and you can feel the coordination in the scale. This is not a single person's project, and it is not a single season's whim. The T-shape is not an abstract accident in the stone, because it repeats with a consistency that reads like intention. Some pillars show carved arms folded forward, hands meeting near the belly, and belts with hanging elements that resemble loincloth-like details. The pillars read as stylized human figures, not simple posts, and that reading changes how we imagine the enclosures. They are not merely spaces with supports, but spaces populated by carved bodies, standing in a circle, facing inward. When you stand at the edge of an enclosure, the effect is uncanny, because the architecture seems to stare back. Relief carvings cover many surfaces with animals and symbols, often rendered in low relief that catches oblique light. Foxes, boars, snakes, scorpions, birds and aurochs appear repeatedly across the complex, each species chosen with enough consistency to suggest more than decoration. Some animals are shown in profile with careful anatomy, while others are abstracted into powerful outlines. The limestone becomes a screen for a world of teeth, horns and movement. Under shifting sunlight, a carved flank can seem to move, and a snake can seem to slide along the stone. Iconography matters here because it signals shared meaning across multiple building phases, and shared meaning implies social connection. The animals are not random decoration, and they cluster in recurring combinations that look patterned rather than improvised. Some scenes suggest motion, confrontation, or guarding, as if the walls are staging a drama that the living participants understood. Abstract marks appear alongside the animals, including H-like signs and crescents, and their repetition hints at a vocabulary we cannot yet translate. The fact that we cannot translate it is not failure, because the carvings still tell us that communication was being externalized into durable form. The carvings are precise enough to imply specialist skill and long practice, even if that specialization was seasonal rather than full-time. In small-scale societies, skill can be concentrated without rigid class structure, and mastery can be recognized through ritual authority. A person who can carve stone convincingly may also be a person who can lead a ceremony, or preserve a story, or mediate disputes. The art is not just art, it is social technology made visible. It turns memory into surface, and surface into a shared reference point. The disruptive element is scale, not mystery, and scale is the part we can estimate without guessing beliefs. Standard models once placed monuments after agriculture, surplus, and settled villages, because surplus seems like the fuel that powers large projects. The usual sequence runs farming to storage to hierarchy, to cities to temples, a chain that feels logical when read backward from later civilizations. Göbekli Tepe appears to invert that sequence, because it looks like a temple complex before widespread farming is thought to dominate. The inversion is not a minor adjustment because it changes what we think humans need before they can build big. That inversion forces a simple question about labour, and labour is measurable in stone. Quarrying, transporting and raising multi-ton pillars requires coordination, and coordination implies shared schedules, shared goals and repeated cooperation. It requires planning, repeated effort, and some form of leadership or consensus that can persist beyond a single day. It also requires feeding workers during construction and maintenance, because hungry people do not haul limestone for long. Even if the work was episodic, the social machinery had to be reliable enough to restart again and again. For decades, many assumed only farming could support that kind of project, because farming can store calories and stabilize expectations. The assumption was not irrational, because agriculture does create storable surpluses and the possibility of supporting non-food specialists. Yet assumptions can harden into invisible rules, and invisible rules can make real evidence feel impossible. Göbekli Tepe forces the model to bend because the stone is already standing there. The question becomes not whether it exists, but how the social engine was built. Mainstream archaeology did not respond by claiming lost technology, because the tool traces and materials do not require it. It responded by revising what hunter-gatherers can organize, and by taking social motives as seriously as material constraints. The leading interpretation frames Göbekli Tepe as a ritual center built by foragers, not a permanent city built by farmers. Groups could gather seasonally, cooperate intensely, and then disperse again, returning to mobile lifeways when the gathering ended. Social complexity can exist without permanent towns if ritual binds people strongly enough, especially when identity and alliance are at stake. Feasting becomes a key mechanism in this model, because feasting turns food into politics and memory. Large gatherings can be motivated by ceremony, alliance, marriage arrangements, and competition, and each motive can reinforce the others. Feasts require food, and food demands procurement at scale, whether through hunting drives, mass harvesting of wild cereals, or the careful scheduling of seasonal abundance. That pressure can push people toward managing resources more intensively, even before full domestication takes hold. In other words, a ritual calendar can begin to shape an ecological calendar. On screen, reconstruction can show people arriving in small groups, carrying hides, baskets, and stone tools, converging on the ridge like tributaries. Fires bloom in the dusk, and the air thickens with smoke and roasting meat. The camera can cut between hands grinding seeds and hands lifting stone, because both are forms of work, and both leave traces. In the background, the carved animals are not silent decorations, because they frame the gathering like witnesses. In this view, monuments can catalyze sedentism rather than result from it, and that reversal is the chapter's pivot. A fixed ritual center creates a reason to return, and return visits create familiarity with the landscape's rhythms. Familiarity encourages storage, and storage encourages staying longer, and staying longer changes social expectations. The steps toward farming can be gradual, and the monument can sit near the beginning of that slope. Once people invest in a place, the place begins to demand maintenance, and maintenance begins to demand predictability. The site sits within a region that soon shows early farming and herding, and that regional context matters because Göbekli Tepe is not isolated in a vacuum. Nearby settlements and landscapes record the Neolithic transition unfolding over millennia, with changes visible in seeds, bones, and settlement patterns. Wild cereals and game were abundant, then gradually managed and domesticated, as people began shaping ecosystems rather than simply moving through them. Climate stabilization after the Younger Dryas likely widened the window for predictable harvests, and predictability is a powerful incentive. When a harvest can be anticipated, it can be planned around, and planning is the seed of permanence. The early Holocene did not create ease, but it changed the rules in ways that mattered for risk. Warmer temperatures and shifting rainfall patterns altered growing seasons, water availability, and the distribution of animals, and those changes ripple into human choices. When the environment becomes more reliable, investment in place becomes less risky, and the calculus of mobility shifts. Yet reliability can also raise stakes, because more people can cluster in the same productive zones. When more people cluster, the need for shared rules becomes sharper, and ritual can become one of those rules. This is where environment joins architecture without reducing it to climate alone, because humans are not thermostats. The Younger Dryas ends and the Holocene begins with shifts in temperature and rainfall patterns, and those shifts reorganize plant communities, animal ranges and seasonal water sources. Societies respond by changing mobility, storage and social networks, and those responses can be creative rather than merely reactive. Stress and opportunity can both intensify coordination, because both can make cooperation feel necessary. A monument can be a response to abundance as much as to scarcity, because abundance creates competition over access. On screen, the narrative can show this as layers, like pages turning under a hand. First, a cold, dry steppe with sparse growth and long shadows, where survival feels narrow and seasonal. Then, gradually, a greener mosaic appears, patches of grass, stands of trees, and more consistent water in low places. The ridge of Göbekli Tepe remains, but the world around it becomes more productive, and productivity changes what gatherings can sustain. The camera can return to the same ridge in different seasons, emphasizing that time is not only years, but cycles. Göbekli Tepe still feels like an anomaly, because it is not a small shrine, and it does not look like a one-off experiment. It is a complex with multiple enclosures, rebuilt and modified over time, with evidence of repeated construction episodes rather than a single burst. The construction sequence suggests planning across generations, because walls are repaired, pillars are replaced, and spaces are reconfigured. The repeated T-pillars imply a stable symbolic system, and stability implies teaching, memory, and continuity. A stable system also implies enforcement, because symbols do not stay consistent by accident. The labour investment implies a reason strong enough to persist, and persistence is the part that should slow us down. People do not return to the same ridge for centuries without a motive that outlasts individual lives. That motive could be religious in the broad sense, but it could also be social in the most practical sense. An anchor for alliances, a place to manage conflict, and a stage where legitimacy is performed. Monumentality can be a tool for making agreements feel permanent, because stone does not argue back. The very weight of the pillars can become a metaphor for the weight of obligations. Archaeologists emphasize that the site is not clearly a village, and that distinction shapes every interpretation. Domestic architecture is limited compared to later Neolithic settlements, where houses, storage rooms, hearths and middens dominate the plan. Evidence for everyday living exists but does not dominate the layout, and that imbalance suggests the primary function was not ordinary residence. The enclosures feel purpose-built for gatherings and ritual performance, where bodies assemble and attention is directed. A ritual space is not just where people stand, but where people are made to look, listen, and remember. That separation strengthens the ritual center interpretation, because it implies a deliberate choice about space. A village grows by accretion, with messy edges and practical constraints, because daily life is improvised. A ritual enclosure, by contrast, can be laid out with geometry, symmetry, and controlled access, even if the geometry is not mathematically formal. At Göbekli Tepe, the circles and ovals feel like designed arenas, where the architecture shapes what people see and how they move. You can imagine the crowd's attention being pulled toward the central pillars, as if the space itself is directing the ceremony. The most unsettling feature is not the building, but the unbuilding, because it looks like a choice. Many enclosures were deliberately backfilled in antiquity, and the act looks intentional rather than accidental. The fill is not simple wind-blown sediment accumulating slowly over centuries, because its contents are mixed, and its deposition looks rapid. Excavators describe deposits with stone fragments, animal bones and debris, as if material was gathered and dumped into the spaces. The result is a strange kind of preservation, where the architecture survives because it was hidden. Stratigraphy suggests purposeful infilling rather than gradual abandonment, and stratigraphy is the site's quiet witness. Layers tell time not by dates alone, but by the order of events, the compaction of sediments, and the way materials are jumbled or sorted. When fill is dumped quickly, it can trap artifacts in chaotic orientations, and it can create a signature distinct from slow natural accumulation. In the case of Göbekli Tepe, that signature repeats. Repetition is important here, because it argues against a single accident or a single storm. Purposeful burial is the leading view because the pattern repeats across multiple enclosures, and because the deposits look curated rather than random. Walls and pillars were covered, and new structures were sometimes built nearby, as if closure and renewal were part of a cycle. The fill composition looks like material gathered and dumped intentionally, including refuse that may have come from feasting or daily activity elsewhere. The act required labour comparable to construction. Because moving volume is always expensive in human time, it is hard to imagine such effort without a shared reason. Even if that reason is now silent, someone decided these spaces should be sealed, and that decision is as important as the initial building. Construction is a statement, but burial is also a statement, one that changes how future visitors encounter the place. A standing monument broadcasts itself across the landscape, inviting approach and interpretation. A buried monument withdraws, leaving only a mound and a memory, and memory can be controlled. The hill becomes a kind of edited archive, where the pages are not torn out but deliberately closed. That decision opens a narrow space for tension, handled carefully, because motives are easy to dramatize and hard to prove. Burial can be practical, stabilizing structures and creating level ground for new building, especially if walls were weakening or if pillars needed protection from weathering. Burial can be symbolic, closing a sacred place after its use ends, like extinguishing a fire in a controlled ritual. Burial can also be protective, preserving what mattered from vandalism, conflict, or the slow violence of erosion. Each motive fits the physical act, and the physical act is what we can actually observe. The evidence supports intention, but intention has multiple plausible motives, and we should not pretend the stone whispers a single answer. We must not claim fear when the record cannot prove fear, because fear is a story we can project too easily. Still, the act of sealing monumental enclosures invites questions about cultural memory, and memory is often managed through ritual acts. Why hide the pillars instead of letting them stand as markers, visible to anyone passing the ridge? Why erase visibility while preserving the forms under sediment, as if the goal was survival without display? What kind of society builds a monument, then chooses silence? The choice suggests a controlled ending, not a chaotic collapse, and controlled endings are culturally meaningful. Controlled endings imply shared agreement about when a chapter closes, and shared agreement implies authority or consensus. They also imply that the builders expected a future, even if they did not imagine us. A place is sealed because someone cares what happens after sealing, and because someone believes the act of sealing matters. In that sense, the backfill is not just dirt, but a deliberate gesture. In a documentary about detectability, that matters because it shows how disappearance can be manufactured. Earth erases by grinding and recycling, but humans can erase by design, and design can mimic absence. A deliberate burial is a human-made unconformity, a curated layer that interrupts what we think we should see. It turns architecture into a time capsule, even if the builders never used that concept, and it complicates the idea that absence means nothing happened. The mound becomes both a hiding place and a preservative, like a sealed jar in a pantry. The site becomes a metaphor for the whole series, because it shows how survival can be paradoxical. A civilization could vanish and leave only chemistry and rock, and the chemistry might be ambiguous without context. A society could also choose to bury its own evidence, leaving future readers guessing at motives and timelines. In both cases, the record becomes indirect, and we infer behaviour from residues, patterns, and what is missing. The past is not only what happened, but what was allowed to remain visible. Göbekli Tepe does not prove a prior industrial world, and it does not need to, because its power is already sufficient. It does not even require a lost high technology to be astonishing, because the astonishment is already in the social feat. It proves that coordinated monumentality can appear early, under conditions we once labelled too simple. It proves that our timelines are models, not laws, and models must answer to stone. The pillars are not arguments, but they function like evidence in a trial, forcing the story to adjust. It also proves that culture can reorganize quickly after disruption, because calendars and expectations can change fast. The end of the Younger Dryas is not just a line on a graph, but a shift that would have changed seasonal expectations and resource calendars. When calendars change, rituals often change too, because rituals are ways of synchronizing people with each other and with time. A monument can be a calendar made of limestone, even if we do not yet understand its schedule. It can mark not only seasons, but obligations, who must come, when, and why. The broader theme returns through a different doorway, because knowledge can survive without machines. Knowledge can survive disruptions without leaving obvious technology, because knowledge is not only technical and not only written, it can survive as ritual practice, shared symbols and construction techniques, transmitted through apprenticeship and repetition. It can also survive as a social technology, the ability to mobilize people, to resolve disputes, and to coordinate labor without formal bureaucracy. Those are invisible skills until they suddenly become visible in stone. When those survive, stone can appear before the story expects it, and that is the lesson we should carry forward. A community can be materially simple yet socially intricate, and social intricacy can build heavy things. The temptation is to equate complexity with metal, writing, and cities. But Göbekli Tepe warns us that complexity can wear other masks. The mask here is carved limestone under a hill, and the mask is heavy enough to change textbooks. It asks us to separate technological complexity from organizational complexity, because they do not always rise together. We should also name what Göbekli Tepe is not, because boundaries keep speculation honest. It is not a city with streets, bureaucracy and dense housing, where administrative needs drive monumental display. It is not a factory landscape with slag, mines and chemical residues, where industrial processes leave unmistakable signatures. It is not evidence of metallurgy or industrial emissions, and it is not a deep-time carbon spike hiding in ice cores. The site's strangeness is human, not mechanical, and that distinction matters. Yet it still presses on the central question by analogy, because it shows how easy it is to underestimate the past. If even recent prehistory can surprise us with early monumentality, then deep time is even more dangerous because deep time has had more chances to erase. The geological record is a shredder with a few pages left intact, and those pages are scattered. Archaeology is also a shredder, just with smaller teeth, because most human materials decay quickly. Wood rots, fibers vanish, and even bone can dissolve, leaving stone as the loudest survivor. A missing chapter can be created by erosion, sea level, or deliberate burial, and each mechanism removes different kinds of evidence. Sea level rise can drown coastal settlements, and later sediments can bury them under meters of mud. Erosion can strip a landscape down to bedrock, removing the very layers where people lived. Deliberate burial can hide what would otherwise stand as an obvious marker. When we look for beginnings, we are often looking for what survived, not what existed. The iconography adds another layer to that analogy, because symbols are a different kind of residue than tools or bones. The carvings look like a symbolic system shared across groups, and shared systems imply communication beyond a single band. Symbolic systems can transmit information without writing, because they can encode rules, identities and warnings in durable form. If a crisis reshaped the world, symbols could carry memory when infrastructure fails. Even without a script, a repeated sign can function like a boundary marker in the mind. The question becomes uncomfortable in a productive way, because it forces us to think about what people choose to preserve. What kinds of memories do people choose to carve into stone, and what kinds do they keep in stories that can vanish? What is the threshold at which a community decides that memory needs a more durable medium? The pillars do not answer, but they make the question unavoidable. They suggest that something, belief, obligation, identity, was important enough to deserve permanence. We do not need to assert a specific catastrophe at Göbekli Tepe, and restraint is part of the method. The climate context is enough to show instability near the transition, and instability can be social even when it's not apocalyptic. The end of the Younger Dryas and early Holocene shifts could reorganize subsistence and settlement, pushing groups to renegotiate territories and alliances. That reorganization could elevate ritual as a stabilizing force, because ritual can make uncertainty feel structured. When the world is changing, a fixed place can become a psychological anchor. Ritual can be a technology for surviving uncertainty, and that is not a metaphor, because it has measurable social effects. Ritual synchronizes behavior, reduces conflict during gatherings, and creates shared expectations that outlast the moment. In a world where resources fluctuate and groups meet seasonally, predictable ceremony can be as important as predictable rain. The architecture at Göbekli Tepe may be the physical scaffold for that predictability. The circles do not just hold pillars, they hold people in a shared pattern. The mainstream model remains cautious and testable, and its strength is that it makes specific claims we can look for. Hunter-gatherers can build monuments when social incentives are strong, and the incentives can be traced through faunal remains, tool assemblages, and patterns of repeated construction. Feasting and ritual can drive resource management and encourage staying in one place longer, and those shifts can be tracked in plant remains and settlement density. Over time, those pressures can contribute to domestication and farming, and domestication leaves signatures in seed size and animal bones. The point is not romance, but evidence that can accumulate. In that framing, the temple comes first, and the fields follow, and the phrase matters because it flips causality. That reversal is not just a clever line, because it changes how we imagine motivation in human history. It suggests that ideas, obligations, and shared identities can be drivers, not merely reflections of economic change. It suggests that belief and social structure can create the conditions for agriculture, rather than agriculture creating belief. If that is true here, we should be careful about treating later sequences as universal laws. This model still leaves an emotional residue of anomaly, and that residue is part of why the site grips the public imagination. We are trained to expect stone to follow surplus, not precede it, because later civilizations make that pattern feel universal. We are trained to expect complexity to rise smoothly, not jump, because smooth curves are easier to teach. Göbekli Tepe looks like a jump, even if the mechanisms are human. It is a reminder that our charts often show what we have found, not what once existed. The shock is not supernatural, it is chronological, and chronology is the part that refuses to be argued away. The date range places these enclosures very early, close to the threshold where we stop expecting large formal architecture. When a threshold is crossed, it forces us to ask whether the threshold was real or merely a habit of thought. Göbekli Tepe does not break physics, but it breaks a storyline. It forces us to imagine that social ambition can precede economic transformation, and sometimes even cause it. Then the burial returns as the chapters hinge, and it deepens the mystery without requiring fantasy. A buried monument is a message with its volume turned down, and the quietness is intentional. It survives because it is hidden, not because it is celebrated, and that inversion is psychologically striking. It suggests that preservation can be intentional, and that closure can be engineered with as much care as opening. The act of backfilling becomes a kind of authorship, editing what the future is allowed to see. If we allow a careful speculative edge, it stays framed as possibility rather than proclamation, because the record has limits. A community might seal sacred space to protect it from an approaching change, whether environmental, social, or political. A community might bury it to mark an ending they did not want repeated, turning closure into a warning. A community might hide it because the meaning became dangerous, or because the site's power needed containment. The important point is not the drama, but the recognition that humans can curate their own archaeological footprint. None of these are proven, but all are compatible with intentional backfilling, and compatibility is not the same as certainty. The point is not to choose a dramatic motive, but to recognize that motives exist, and that motives shape what survives. When we excavate, we are not only uncovering stones, we are uncovering decisions. Those decisions sit between us and the past like a filter, and the filter can distort what we think we are seeing. The documentary's larger logic tightens around this point, because detectability depends on survival. Detectability depends on what survives, and survival depends on both geology and behavior, which is why the record can mislead. A pre-human industrial civilization would leave chemical shadows more than artifacts, because artifacts corrode and landscapes recycle. A human pre-agricultural society can leave stone shadows more than settlements, because stone endures while wood, fibre and skin vanish. In both cases, the surviving trace can be real and still incomplete. In both cases, the surviving trace can mislead us about the true scale of what existed, and that is the caution. A small amount of evidence can represent a large amount of activity, if most of the activity leaves no durable residue. Conversely, a dramatic monument can make a society seem more materially advanced than it was, if we equate monumentality with industry. Göbekli Tepe teaches caution in both directions. It invites us to ask what else we have misread, simply because the surviving materials are biased. Göbekli Tepe also reminds us that beginnings are often constructed after the fact, and that origin stories are tools. We like clean origin stories because they simplify causality, and because they make the past feel like a straight road to the present. We like farming as the start because it is measurable in seeds and bones, and because it looks like an obvious turning point. We like cities as the start because they leave walls and texts, and because texts tell us what to think, but the real process can be messy, with ritual, gathering, and monumentality entangled early. The first durable stones may mark social transformations that happened before crops were fully domesticated, and that possibility changes our sense of sequence. The first large projects may be responses to uncertainty, not celebrations of stability, because uncertainty can demand coordination. The past does not always arrange itself into our categories, and categories can become blinders. When we see stone, we should not automatically assume the economic system that later stone implies. We should ask what kind of social pressure could make stone feel necessary. This is the bridge to Egypt, where official beginnings feel especially neat. Egypt offers stone that seems to arrive with a fully formed state, and the suddenness can feel almost theatrical. It offers monuments that appear to spring from a mature ideology, complete with divine kingship and cosmic order. It offers a narrative of sudden order, then long continuity, as if the script was written in advance. Yet if Anatolia can surprise us, then the Nile deserves the same skeptical patience. If early monumentality is possible, we must ask whether later timelines are too polished. If a ritual centre can precede agriculture in Anatolia, then the appearance of full-scale monumentality elsewhere deserves careful scrutiny. Are we seeing true beginnings, or are we seeing the first surviving chapters after earlier pages were lost? Stone can be honest, but it can also be selective. It can preserve what was buried, and it can erase what was built in wood and mud. We end by turning the question from possibility to scrutiny, because scrutiny is the method that keeps wonder disciplined. If Göbekli Tepe can exist before agriculture is widespread, then what else can exist before our categories allow it, hidden in plain sight? If a site can be deliberately buried, then what else can be deliberately hidden, sealed under sediment by human choice? If stone can be older than the story told about it, then the next chapter must test the story against the stone. The goal is not to inflate mystery, but to refine our sense of what the record can conceal. We follow the trail from Anatolia to the Nile, where the official dawn of civilization may not be the first light. The hook returns quietly, not as a claim but as a method, and methods are how mysteries become knowledge. If something was here before us, the planet would erase its footprints, because time is relentless and landscapes are hungry. It might still leave a few fingerprints, and sometimes those fingerprints are carved into pillars, sometimes they are buried on purpose, waiting for us to notice how strange the timing feels. Egypt is where stone becomes policy, where a monument can harden into a calendar, and where disagreement feels almost like heresy. The monuments feel eternal, and the dates feel settled, until you ask how settled is settled in a landscape reused for millennia. In a place where kings wrote themselves into limestone, even uncertainty can sound like an accusation, because it threatens the order the stone was meant to guarantee. We have been chasing fingerprints in chemistry and scars in sediment. Now we stand before a face cut from bedrock, and the argument turns personal. The camera does not need to invent drama here, because the drama is already carved into the plateau and lit by the same sun that lit ancient processions. A single figure, half animal, half sovereign, forces us to ask what counts as evidence when the evidence is also an icon. The Great Sphinx sits on the Giza Plateau, carved from limestone left in place. It is not a transported statue, it is a landscape turned into an image, with the bedrock itself drafted into royal symbolism. The body emerges from the plateau like a ridge that learned to breathe, while the head rises above the enclosure walls like a command. From a distance it looks serenely finished, but up close the surface is a palimpsest of damage, patching, and time, chips, crusts, mortar seams and the soft rounding of edges. Official chronology places it in the Old Kingdom, around 2500 BCE. The standard attribution ties it to Pharaoh Khafre and his pyramid complex, which dominates the plateau with a kind of engineered inevitability. In that reading, the Sphinx is not an orphaned marvel, but a deliberate statement in a carefully planned ritual terrain. It becomes a signature piece of a state that had learned to project authority through stone, geometry, and controlled movement. This is the orthodox spine of Egyptian history, and it is built from many bones, not one. Pre-dynastic cultures consolidate, dynasties begin, the state forms, and stone architecture accelerates as administration grows more capable. The Nile's predictable flood cycle underwrites agriculture, and agriculture underwrites administration, and administration underwrites the ability to mobilize labor on command. In that chain, monuments are not only art, but logistics made visible. Food stores, work schedules, quarry routes, and social hierarchy turned into architecture. By the 4th dynasty, Egypt builds at scale, and it builds with a confidence that still intimidates modern eyes. The Great Pyramid, Khafra's Pyramid, and Menkaur's Pyramid anchor a sequence of royal projects, each one refining techniques of surveying, hauling, and stone dressing. Their alignments, quarry scars, and worker settlements suggest not improvisation, but a mature system of planning that could feed crews and coordinate specialists. When you stand on the plateau at dawn, the pyramids catch first light like geometric cliffs, and the desert air makes their edges look unnaturally sharp. In that framework, the Sphinx is one component in a planned sacred landscape. Causeways, temples, and quarrying patterns link monuments into one program, with sightlines that choreograph what a visitor is allowed to see and when. The plateau reads like a diagram of procession, where movement from river to valley, temple to pyramid becomes a ritual narrative. The Sphinx sits near that narrative like a guardian placed at a threshold, silent, but positioned like an argument. Mainstream dating is not a single method, and it is not a single authority speaking with one voice. It is a convergence of context, stratigraphy, tool marks, inscriptions, and stylistic comparison, each one imperfect but valuable when they agree. Each line has weaknesses, but the hope is that weaknesses do not align in the same direction and create a shared illusion. The method is less like a stopwatch and more like triangulation in fog, where you accept a probable window because the alternatives fit worse. Start with context, because context is the first clock archaeology trusts. A monument is dated by what it is connected to, what it is built into, and what later structures cut through or respect. If a structure is physically integrated with a complex that can be dated, it inherits a probable window, like a page bound into a known chapter. The logic is simple in principle, yet fragile in practice, because landscapes are reused for centuries and later builders can imitate earlier forms. The Sphinx is surrounded by the Sphinx Temple and the Valley Temple. Those structures use massive limestone blocks, some likely quarried from the Sphinx enclosure, which would make the trench both a sculpture site and a source quarry. The blocks are not small bricks, but megalithic slabs with rough faces and squared edges, stacked like a geology lesson turned architectural. In the temples, you can feel the weight of decisions made by engineers who understood stone, friction, and the limits of muscle power. If blocks came from the enclosure, then the quarrying, carving, and temple construction are part of one operational episode. That episode is placed within Khafra's complex, where the Valley Temple's layout and masonry style fit 4th dynasty patterns. The argument is not that every block must match perfectly, but that the overall pattern fits a coordinated build with shared labour and shared planning. It is a picture of a workforce cutting, hauling, and setting stone in a tight sequence, with waste piles and work areas forming a kind of industrial footprint. Causeways matter because they are engineered links, and engineered links carry administrative fingerprints. A causeway ties a pyramid to a valley temple, and it ties ritual movement to a specific reign, because these corridors are expensive and politically meaningful. These are not casual paths worn by feet, but constructed passages with walls, paving, and controlled sightlines that frame the king's monument as you approach. They are infrastructure for ceremony, and infrastructure is rarely anonymous. Someone paid for it, supervised it, and claimed it. Stratigraphy matters because layers have order even when dates are missing. If a wall cuts a layer, it is younger than that layer, and if a floor seals debris, it is younger than the debris beneath it. If a repair overlays an earlier surface, it admits a sequence of interventions, even when the repairs try to hide their own seams. This is the quiet power of stratigraphy. It does not tell you the year, but it tells you the direction of time. At Giza, excavated deposits around temples and ramps can be read as construction layers, including levelling fills and work debris. They can also be disturbed, which is why the reading stays cautious and why careful recording matters as much as discovery. Ancient builders reworked ground, later visitors dug pits, and modern excavations introduced their own footprints in the form of trenches and backfill. The plateau is not a sealed capsule, but a stage that has been reset many times, with each reset blurring earlier edges. Toolmarks matter because technology leaves habits, and habits are surprisingly diagnostic when you know what to look for. Old Kingdom stoneworking has recognisable patterns in dressing, pounding and smoothing limestone, including the textures left by dolerite pounders and the linear traces of copper chisels. A chisel stroke has a rhythm, and a pounder leaves a texture, and a finished face reflects a choice about time and labour. Even when names are absent, the work can still speak in a language of technique. Copper tools, stone pounders and abrasive sand can shape limestone efficiently, especially when teams are organised and tool maintenance is constant. The absence of iron does not prevent precision, but it constrains certain cuts and increases the importance of abrasives, which do much of the actual grinding. Copper is softer than many stones, yet it can be hardened by hammering, and it can be used with sand as an abrasive that does the real cutting. In plain terms, the tool is often a handle for grit, and the grit is the blade. Quarry marks and work gang traces matter when they exist, because they hint at organisation and sometimes preserve the human scale of the operation. In some contexts, marks can link blocks to crews and to administrative systems, showing that labour was divided, tracked and rewarded. At other sites, we see names of work teams, tally marks and symbols that function like a construction ledger, sometimes even invoking royal names as a kind of brand. Even when Giza's evidence is uneven, the broader Old Kingdom pattern shows a state that tracked labour carefully, because feeding workers is as critical as commanding them. Inscriptions matter most when they are in primary context, where a mark is still on the stone where it was first placed. A name on a block can be decisive, unless the block was reused or moved, which is common in a landscape where old stone is valuable. Egypt reused stone often, especially in later periods when old monuments became convenient quarries for new projects. A carved cartouche can travel, and when it travels it becomes a trap, because it looks like a signature even when it is only recycled material. At the Sphinx itself, direct inscriptions naming Khafra are limited and contested. The strongest mainstream case is contextual, not a single carved label that ends the debate in one stroke. That distinction matters, because context can persuade without ever delivering a definitive signature, and persuasion can harden into certainty through repetition. It is a courtroom built on circumstantial evidence, where the jury is asked to trust the coherence of the scene. Stylistic analysis is another line of evidence, and it works by comparison rather than measurement. The head's proportions, the Nemes headdress and royal iconography are compared to 4th dynasty conventions, including the way faces are idealized into calm authority. The face is read like a portrait, with cheekbones and mouth lines treated as historical clues, as if stone could preserve a dynasty's preferred look. Yet portraits can be idealized, and idealization blurs individual identity, especially when later repairs may have softened or sharpened details. But style is a soft clock, and soft clocks can drift without anyone noticing. Style can be conservative, revived, or altered by later restoration, and the Sphinx has been repaired repeatedly across dynasties and modern conservation campaigns. A recarved edge can mimic an older fashion, and a missing detail can be the result of damage rather than design. The head we see is not necessarily the head that was first finished, and that uncertainty matters when style is asked to carry dating weight. This is where the official date becomes a problem of method. The date is plausible, but plausibility is not the same as proof, especially when the object is unique and the context has been disturbed. In a discipline that rarely gets perfect timestamps, plausibility can harden into certainty through repetition, lecture slides, and museum labels. The question is not whether the orthodox model is reasonable, but whether it is constrained tightly enough to resist a serious anomaly. Now the controversial argument enters, and it enters through the body, not the face. The Sphinx enclosure shows weathering that some read as water-driven erosion, and the claim begins with what the camera can see. The camera lingers on the walls of the trench, where the limestone looks less like a clean cut and more like a shoreline. The surface is not simply rough, but sculpted into curves and recesses, with vertical waviness that seems to ignore the straight intentions of quarrying. The claim is simple and explosive, because it proposes a climate where we do not expect one. The vertical undulations and rounded profiles resemble rainfall runoff, not just wind and sand abrasion, and they appear on surfaces that would have been exposed in the enclosure. Instead of sharp, angular fluting, the walls show softened forms that some interpret as water's patient handwriting, repeated season after season. If that handwriting is real, it implies a different sky above ancient Giza, cloudier, wetter, and persistent. If rainfall shaped those walls, then the carving could predate dynastic Egypt. It could reach back to a wetter climate, possibly the early Holocene or earlier, when North Africa experienced stronger monsoonal influence. The early Holocene, after the last ice age, brought stronger African monsoons that pushed moisture north. In that time, the Sahara was not the Sahara we imagine, but a landscape with grasslands, lakes, and seasonal rivers, where animals and people moved through corridors now erased by dunes. This is the lost civilization narrative's opening, and it is powerful because it reverses a familiar story. If the Sphinx is older, then Egypt's Stone Age begins with an inheritance, not an invention, and the Old Kingdom becomes a revival rather than a beginning. The pyramids become not the first leap but a later refinement of something already known, perhaps repurposed for a new political theology. The plateau becomes a museum built over a forgotten workshop, with later kings claiming the credit of deeper time. Supporters point to paleoclimate, because climate is a clock written across continents and recorded in multiple archives. The Saharan Nile region experienced stronger monsoon phases in the early Holocene, with lakes and greener corridors that are still visible in ancient shorelines and lakebed sediments. Sediment cores, fossil pollen, and ancient drainage patterns suggest periods when water lingered where dunes now roam, changing soils and vegetation. In that greener interval, rainfall could be not a rare event, but a repeated seasonal force capable of shaping exposed rock. They argue that sustained rainfall capable of carving deep channels is inconsistent with the arid Old Kingdom. They suggest a timeline mismatch written into limestone, as if the stone is quietly contradicting the texts. The Old Kingdom was not rainless, but it was not a monsoon regime either, and the difference matters for cumulative erosion. The claim is not about one storm, but about repeated wetting and runoff over centuries, the kind of persistence that leaves rounded profiles rather than sharp cuts. They also argue that the Sphinx head looks too small for the body. They propose recarving, where an older lion-like form was reshaped into a royal face, compressing the original proportions. The idea is that a larger head, perhaps more feline, was reduced to fit a later political need, with the Nemes headdress becoming a kind of overprint. In that scenario, the body's weathering becomes a relic of an earlier design, while the head becomes a later edit. That claim is not just about aesthetics, and it is not only about proportions in photographs taken at odd angles. It is an attempt to explain why the body's erosion looks older than the head's surface, as if two exposure histories are stitched together. If the head was reworked later, it would present fresher tool marks and less time for decay, especially on sharper features. The Sphinx would then be a hybrid artifact, with different ages locked into one silhouette, an archaeological chimera. Mainstream scholars respond with a different set of mechanisms, because geology rarely offers only one path to a similar shape. Weathering is not a single process, and limestone is a complicated recorder that reacts to chemistry as much as to impact. Limestone is layered, porous, and chemically reactive, and it can fail in ways that look deceptively like water carving. The same wall can hold several histories at once, because the rock itself is not uniform from layer to layer. Differential erosion can mimic water patterns, especially in sedimentary rock with variable hardness and variable cementation. Softer layers retreat faster, harder layers stand proud, and the wall can develop vertical relief without rainfall, simply by uneven decay. If bedding planes run horizontally, the wall can break into steps and grooves as weak bands crumble and stronger bands resist. From a distance, those grooves can resemble channels, even when they are layer-controlled and driven by microfractures. Salt exfoliation is a major agent in arid zones, and it is brutal in slow motion. Salts crystallize in pores, expand, and pop flakes off the surface, creating rounded forms over time and leaving a scaly texture that can look like water smoothing. This is not dramatic flooding, but microscopic pressure repeated thousands of times, driven by humidity cycles and evaporation. In close-up, the stone looks as if it is shedding thin shells, and each shell is a tiny loss of history. Groundwater can rise and fall, bringing dissolved salts into stone and concentrating decay where evaporation is strongest. Capillary action can draw moisture upward through porous limestone, then leave salts behind as the water evaporates in the heat. This can focus damage at specific heights, producing banded deterioration that looks like a tide line that never quite disappears. The Sphinx enclosure has long interacted with subsurface moisture, especially as the local water table changed with irrigation, modern development, and seasonal variation. Wind erosion is not only sandblasting, and the desert's violence is often subtle. Wind carries dust, drives temperature swings, and accelerates chemical weathering, especially where stone is already weakened by salts and microcracks. Day-night cycles expand and contract minerals, and that stress opens pathways for more moisture and more crystallization. The desert works like a file and a furnace at once, and it does not need rain to be relentless. Restoration history complicates everything, because the Sphinx is not a pristine sample. The Sphinx has been buried in sand for long periods, then excavated, patched, and refaced with new stone, sometimes with mortars that behave differently than the original limestone. Burial can protect surfaces from wind, yet it can also trap moisture and salts against the body, creating hidden decay. Excavation exposes fresh faces to a harsh microclimate, sometimes abruptly, like opening a sealed container into dry heat. Each intervention changes drainage and microclimate. Cement, mortar, and replacement blocks can trap moisture, redirect runoff, and create new decay patterns that resemble older weathering, even when they are modern side effects. A repair meant to save the monument can unintentionally create a moisture boundary that accelerates damage nearby, because different materials expand and breathe differently. The Sphinx becomes an experiment with many uncontrolled variables, and the variables are layered like the repairs themselves. So the argument becomes a fight over interpretation, not a fight over whether erosion exists. Both sides agree the stone is damaged, they disagree on what it means, and meaning is where chronology hides. The disagreement is not only scientific but psychological, because the stakes are narrative and identity. If the Sphinx is older, textbooks wobble, and if it is not, the mystery still refuses to die, because the weathering still looks like a question. Geologists ask what patterns match known processes, and they demand mechanisms that can be tested with mapping, sampling, and comparison to analog sites. Archaeologists ask what patterns fit the cultural and architectural context, and which inferences stay disciplined when evidence is incomplete. The two approaches are not enemies, but they prioritize different kinds of coherence and different kinds of risk. One wants a physical model that reproduces the shapes, and the other wants a historical model that explains the placement. This is equifinality in stone, a concept that haunts every attempt to read the past from surfaces. Different causes can produce similar shapes, and the record does not label its own mechanism, even when the shapes feel obvious to the eye. A groove does not come with a tag that says rain, wind, or salt, and it never will. The wall is a result, and results can be overdetermined by several processes acting together. If you want an older Sphinx, you must show that arid processes cannot plausibly produce the observed weathering, even when layered rock and salts are considered. You must also show the timing is constrained, not just suggestive, which means translating shape into rate. That means mapping patterns precisely, comparing them to controlled analogues, and demonstrating that alternative mechanisms fail. The burden is not only to propose but to exclude, and exclusion is always the harder part. If you want a 4th Dynasty Sphinx, you must show that the contextual links are robust, and not an illusion created by later rearrangement. You must also show that later repairs do not create false signals, especially where the line between bedrock and replacement is hard to see. That requires careful documentation of restoration layers, mortar chemistry, and the boundaries between original bedrock and replacement stone. The monument has to be separated into episodes, not treated as one uniform surface, because uniformity is the easiest mistake. This is why extraordinary claims are hard to validate even when they are not absurd. They require not just an anomaly, but the elimination of ordinary explanations across multiple lines, including the messy ones that are easy to underestimate. A single strange feature can be a coincidence, a repair artifact, or a misread layer, and the desert is good at producing illusions. Science is conservative here, not because it hates wonder, but because it hates being fooled, especially by patterns the brain wants to see. Dating in archaeology is a discipline of constraints, and constraints are often indirect. It is less about one perfect clock and more about many imperfect clocks agreeing, each one narrowing the plausible window. When several independent indicators converge, confidence rises, even if none is decisive alone. When indicators diverge, the honest answer is often a range, not a year, and that range can feel unsatisfying in front of a monument that looks absolute. Radiocarbon is powerful, but it dates organic material, not limestone carving. At Giza, Organic samples can date occupation and construction phases, not the cut itself, and even then the samples must be securely associated. Charcoal in a mortar mix can date when that mortar was made, yet mortar can be repaired later, sometimes repeatedly. A piece of wood can be old when used, and that old wood effect can shift dates backward, turning a useful tool into a misleading anchor. Optically stimulated luminescence can date when sediments last saw sunlight. It can help time when sand buried or exposed surfaces, which is relevant for a monument that spent long periods half submerged in dunes. It needs careful sampling, because grains must be shielded from light during collection, and the context must be undisturbed. If sediment is mixed by later digging, the signal becomes a blend of exposures, and the method's elegance is undercut by field reality. Cosmogenic nuclids can date exposure of rock surfaces, using isotopes produced by cosmic rays that accumulate when stone is uncovered. They can be informative, but they are sensitive to burial, erosion rates, and complex exposure histories, which are exactly the Sphinx's problem. If a surface was exposed, then buried by sand, then exposed again, the isotopic clock becomes layered and ambiguous. The Sphinx, with its burial cycles and restoration, is exactly that kind of complicated case. In practice, the Sphinx is difficult to date directly, and that difficulty is part of its mystique. The object is stone, the context is disturbed, and the site has been managed for millennia by priests, rulers, archaeologists, and conservation teams. Tourism, conservation, and excavation all alter the environment, sometimes in ways that mimic ancient processes, like changing drainage or concentrating salts. Even the act of saving the monument changes the experiment because it changes what the stone experiences. So we return to basics, because basics are what remain when precision fails. Stratigraphy gives order, context gives association, and association gives a probable window, not a guaranteed birthday. Archaeology often works like this, building a timeline from relationships rather than from absolute numbers, and then testing that timeline against new finds. It is a craft of careful inference, and its strength is cumulative rather than dramatic. Tool marks can show capability, not calendar, and capability is not a date. Inscriptions can show names, not always first construction, because reuse and later additions are common and politically motivated. Even quarry marks can mislead if blocks were moved, and even stylistic arguments can be circular if the style is defined by the very monuments being dated. The Sphinx sits at the centre of these problems, because it is both singular and endlessly referenced. The Sphinx becomes a case study in how science handles mystery, especially when mystery is culturally charged. Mystery is not a license to declare, it is a reason to tighten methods and to be explicit about what is known versus inferred. It is also a reason to document uncertainty openly, because hidden uncertainty becomes a breeding ground for suspicion and sensationalism. When experts speak too confidently, they invite a backlash when details prove messy, and messy details are inevitable at Giza. Still, the emotional force of the alternative story persists, and it persists for reasons beyond data. The Sphinx looks like it belongs to a deeper time than the texts allow, partly because its body is a low eroded mass while its face is a crisp symbol of authority. That contrast feels like a clue, even when it might be an artifact of rock quality and restoration. The monument seems to carry two moods, as if it has lived more than one life, and the desert has edited it unevenly. That feeling is amplified by Egypt's own gaps, because even Egypt's abundance is incomplete. The written record is not continuous, and the desert preserves stone better than it preserves paper, which means power survives more easily than administration. Papyrus burns, rots and disappears, and ink fades even when stone remains. Administrative archives vanish in floods, fires and regime change, leaving kings without paperwork and eras without voices. Even when inscriptions survive, they are selective, and selection is its own distortion. They record victories, offerings, and legitimacy, not the ordinary labour that built and maintained the state, and not the failures that rulers prefer to forget. A wall text celebrates a king's piety, yet it rarely lists the quarry foreman who broke his hands on limestone. The everyday is the first casualty of time, and the everyday is where dates are often hiding. This is the missing chapters problem, and it is not a romantic metaphor. History is not only what happened, it is what survived copying, storage, and political permission, and those filters are harsh. A document can be accurate and still vanish, while a monument can be propaganda and still endure. simply because stone lasts. Survival is not a reward for truth, it is a reward for material resilience and for being useful to later regimes. Egypt's climate preserves tombs, but it also destroys organic libraries in ways that feel unfairly random. A single humid decade can erase a century of documents, especially if storage fails and insects do what insects do. Termites, mold, and water seepage do not care about dynasties, and they do not care about our curiosity. The archive is always one accident away from silence, even in a civilization famous for preservation. Conquest can erase names deliberately, and Egypt offers famous examples of that violence. Dynasties rewrite predecessors, chisel cartouches, and reassign monuments, turning stone into propaganda with a new owner. A king can be removed from history by the careful strike of a chisel, leaving a blank where a name once anchored a date. Even stone can be edited, and edits can be as informative as the original text. So the paradox deepens, and it deepens in a way that feels almost philosophical. Stone lasts, but stone is mute about motives, and fragile records carry names, but rarely survive long enough to be checked. Geology remembers chemistry, not biographies, and it remembers processes without caring about politics. It records water movement, salt cycles, and stress fractures, but it does not record who gave the order or why the order mattered. That is why the Sphinx is such a perfect pressure point for this series. It sits between deep time and human time, and it refuses to be a clean data point even when we want it to be. If the Petm is a chemical whisper in 56-million-year-old rock, the Sphinx is a visible monument with an invisible birth certificate. One archive is microscopic and the other is monumental, yet both can be ambiguous when you demand a single answer. The central question returns in a new key, and it carries a quiet threat. If something was here before us, would we recognize it? Or would we force it into our nearest timeline because uncertainty is uncomfortable? Would we accept a range of uncertainty? Or would we demand a single date because it feels safer and more teachable? The need for a clean story can be stronger than the evidence, and that need can shape what gets called official. Mainstream chronology is not a conspiracy. It is a model built from surviving constraints and refined through debate, excavation, and correction. Alternative chronology is not automatically fantasy. It is a hypothesis seeking tests, and tests are what separate possibility from persuasion. The difference is not attitude, but method, and method is where credibility lives. A hypothesis becomes science when it specifies what would disprove it, and then accepts that risk. The horror for scientists is not that the Sphinx might be older, because older is not inherently impossible. The horror is that the methods that feel solid can still leave a wide uncertainty band, even in a famous and heavily studied place. That band is where confident stories begin to wobble, and wobbling invites opportunists who sell certainty. Uncertainty is honest, yet it is also socially unstable, because audiences often treat it as weakness rather than rigor. Because uncertainty is where stories breed, and stories can move faster than measurements. A gap in evidence becomes a gap filled by desire, and desire can outrun what the record can support, especially when images are compelling. The Sphinx is an ideal canvas for that projection, because it is both familiar and enigmatic, both photographed and still unreadable. It is seen by millions, yet it still feels unknowable, as if the monument is withholding something on purpose. The responsible posture is not to dismiss anomalies, and not to crown them. It is to ask what new measurements could actually discriminate causes, rather than simply adding more opinion to the pile. Better erosion mapping can separate layer-controlled retreat from runoff channels, especially if measurements are tied to bedrock stratigraphy. Better geochemistry can track salt sources and moisture histories in the stone, distinguishing groundwater-driven decay from surface wetting. Better sediment dating around the enclosure can time burial and exposure cycles, which matter because exposure is what lets weathering accumulate. Better documentation of restoration can remove modern noise from ancient signals, including where mortars and replacement blocks change how water moves. High-resolution photogrammetry can create a baseline model of the surface, so future change can be measured rather than guessed. When the monument is treated as data, conservation becomes part of research, and research becomes part of conservation. But even perfect measurements would not give us everything, and this is the quiet limit of science. They could tell us when surfaces were exposed, not who first imagined the form, and imagination is not preserved in pores. They could narrow a window, not necessarily reveal a name because names require texts and texts are fragile. The Sphinx could remain anonymous even if its age became clearer, and that anonymity may be the most honest outcome. This is selective survival as a motif, now made physical. The face endures, the archives vanish, and we argue about the silence, as if silence itself were evidence. And that silence is not unique to Egypt, even if Egypt makes it feel theatrical. It is the default state of the human past, because most human worlds were built from perishable materials, not limestone. Wooden temples rot, mud brick melts back into soil, coastal villages drown under rising seas, and rivers bury camps under meters of silt, sealing them or scattering them beyond recognition. Even a thriving settlement can vanish if it sits in the wrong floodplain, or if later people reuse its materials until nothing is left. When we imagine a missing civilization, we must imagine its taphonomy, the process of becoming invisible, because invisibility has mechanics. So when someone says a civilization is missing, the first question is not why it is missing. The first question is what would have survived if it existed, and what signatures would be durable enough to reach us. An industrial civilization would leave chemical fingerprints more than monuments, because industry changes soils, metals, and isotopic ratios. A pre-dynastic complex society might leave stone alignments, but not texts, and its traces could be thin even if its impact was real. The Sphinx debate becomes a rehearsal for the Silurian problem, even if no one says that phrase out loud. Detectability is not only about whether something happened, it is about what the planet keeps and what later humans destroy. A world can be real and still be archaeologically faint, especially if it built in wood, reed, and mud. The absence of evidence is not proof, yet it is still a constraint, because constraints are the only honest starting point. Now we widen the lens to myth, because myth is what survives when archives fail. When writing is lost, memory becomes portable, repeated, and encoded, carried in rhythm and story rather than in ink. Oral traditions compress events into symbols, because symbols are easier to transmit than dates. Floods become deluges, fires become sky battles, and collapses become moral stories with cosmic stakes, because morality travels farther than logistics. Across cultures, certain motifs recur, and their recurrence is psychologically persuasive. Great floods, lost golden ages, civilizing teachers, and warnings about hubris appear again and again, as if societies keep circling the same fears. The details change, but the emotional architecture stays familiar, and familiarity can feel like confirmation. It is as if human societies keep rediscovering the same kinds of rupture, then turning rupture into narrative structure. That recurrence is not proof of one global event, and it should not be treated as a shortcut. It is a clue that humans remember disruption, and that disruption is common enough to shape narrative templates across time and geography. A flood can be local and still become cosmic in memory, because trauma scales up in retelling. A drought can last a decade and still be remembered as an age, because it changes who survives and who moves. But myth can still be data, if treated carefully and with humility. It can preserve outlines of real stresses, migration, drought, sea rise, and sudden climate shifts, even when the timeline is blurred. The method is the same as with stone, and it is just as strict because interpretation can run wild. You look for convergence across independent lines, and you resist turning one story into a universal key, because universal keys usually break. Egypt itself offers myths of primeval waters and first mounds, and those images are not arbitrary. It offers cycles of order and chaos, where kings restore balance after breakdown, and that balance is framed as cosmic duty. Those stories may reflect ecology as much as theology, because ecology is what people live inside every day. The Nile floods, the desert advances, and stability feels like a victory over a constant threat, one that can return if vigilance fails. So the chapter's climax is not a verdict about the Sphinx, and it is not a dramatic reveal of a hidden date. The climax is the realization that our strongest monuments can still sit on weak foundations of proof, because proof is often perishable. We can measure erosion, but we cannot easily translate it into years, especially when multiple processes overlap. We can map context, but context can be disturbed and reinterpreted, and reinterpretation is part of scholarship. We can read inscriptions, but inscriptions are political. We can build chronologies, but chronologies are only as complete as what survived, and survival is selective. This is the gap between what stone can endure and what history can prove. It is the gap where deep time hides its best secrets and where confident narration has to slow down. And it is the gap that makes the PEP feel more unsettling, not less, because it reframes our confidence. If we struggle to date one monument in a well-studied landscape, what about vanished worlds that left fewer stones and fewer texts? The Sphinx stares across that gap like a witness that will not testify. It forces us to admit that certainty is sometimes a performance, not a measurement, and performance can be mistaken for knowledge. We end by tightening the series hook again, and the hook is a question about traces. If an earlier industry existed, it might leave no pyramids, only an isotope excursion and a metal ratio, a faint chemical bruise in the planet's archive. If an earlier human chapter existed, it might leave a few stones and 1,000 myths. With the paperwork burned and the coastlines rewritten, the question is not only what happened, but what could possibly remain. Next, we return to the planet-scale archive, where chemistry is harder to fake than stories. We ask what fingerprints cannot be carved away even by time. We widen from monuments back to the oldest archive, stories that outlive archives, and voices that outlast stone. Across the world, people tell flood stories, and the count runs into the hundreds. Some are sung, some are carved, and some are whispered in winter houses when the wind sounds like water. They persist because floods are simple to imagine, yet terrifying to endure. An enemy that arrives without an army. Mesopotamia gives us Utnapishtim, warned before the rivers rise, and a boat built against a coming wall of water. The Epic of Gilgamesh preserves the scene in clay, baked hard enough to survive fires and collapses. The biblical tradition echoes a chosen family, a vessel, and a moral accounting that turns weather into judgment. South Asian traditions speak of Manu warned in time, with life preserved through a deluge and order restored afterward. Indigenous American traditions describe waters rising, survivors on high ground, and a world remade with new rules. Pacific traditions remember waves that erase coasts, and islands that change shape overnight, shorelines redrawn in a single violent tide. The shared elements are striking, yet the differences are just as instructive when you listen closely. Many stories include warning, survival by elevation or craft, and a reset of law once the waters retreat. Many include animals, seeds, and the idea that memory must be carried forward like cargo. Yet each tradition anchors the flood to local geography, local ethics, and local social order. A river people imagines channels and mud, while an island people imagines reef lines and sudden silence. A motif is not a timestamp, and repetition is not proof of one global event. Human minds reuse narrative templates, especially for trauma, social cohesion, and moral instruction that must be remembered. Empires borrow stories, trade routes carry motifs, and scribes translate myths into familiar frames to make them travel. A flood tale can be adopted the way a tool is adopted, useful, adaptable, and easy to fit into new hands. Still, convergence can signal that disruption was common enough to become a universal language. Myths can track real geology if we treat them as noisy sensors rather than literal transcripts. After the last glacial maximum, sea level rose by more than 100 meters as ice sheets melted into the ocean. Coastlines migrated inland, deltas drowned, and people watched familiar land disappear in increments that still felt like betrayal. The rate was not constant, and in some centuries it likely accelerated, turning gradual loss into sudden crisis. A local inundation can become a cosmic flood when retold for centuries, especially when each retelling compresses time. Regional megafloods add sharper candidates for living memory, because they arrive fast enough to scar a lifetime. Ice dam failures can release inland seas in days, carving channels and leaving boulder bars like riprap dropped by giants. River avulsions can shift a main channel overnight, abandoning one floodplain and drowning another, and the maps in people's heads become wrong by morning. Tsunamis can run far inland, leaving sand sheets, marine shells, and salt-killed forests that stand grey for years. Storm surges can mimic tsunamis, and the story may not preserve the difference when the outcome is the same. This is the distinction we need: global flood versus global memory, which can look global from inside a village. A truly global flood would demand a global physical layer of the same age, the same signature, and the same stratigraphic position. A global memory can arise from many floods, in many places, at many times, stitched together by human storytelling. The rock record asks for synchronicity, while oral memory preserves meaning over precision. What matters to a community is not the hydrograph, but the lesson that survival required listening. We return to stratigraphy, because rocks quantify what stories compress. Humans narrate disruption in symbols, and rocks register disruption as chemistry and sediment that can be measured. Both are partial records, and both are biased by what survives long enough to be sampled. The planet keeps fingerprints more reliably than footprints, yet even fingerprints can be smeared by heat, pressure, and time. Layers can be eroded, mixed by burrowing animals or altered by groundwater until the original signal is faint. The Younger Dryas taught us how fast climate can flip in human time, as temperatures swung and a rainfall belt shifted. It also taught us how hard it is to prove a trigger when proxies disagree, and when different regions respond on different schedules. Göbekli Tepe showed recovery and reorganization can be rapid, even without agriculture, and that social complexity is not a late invention. Egypt showed how even stone can lack a birth certificate, when context is reused and archives vanish. A block can be ancient, yet its placement can be young, and the difference matters. Now we return to the PEM, the benchmark that started the case file and still refuses to settle. Around 56 million years ago, Earth recorded a sharp negative carbon isotope excursion, a global shift toward lighter carbon. Temperatures rose rapidly by several degrees, and the warming reached poles that should have been buffered by distance. Oceans acidified as CO2 entered seawater, shifting carbonate chemistry and stressing organisms that build shells. Carbonate dissolved as the CCD shoaled, meaning the depth where carbonate survives moved upward and erased sediments below. Recovery took tens to hundreds of thousands of years, consistent with slow weathering feedbacks that pull carbon back down. In plain terms, the planet has breaks, but they are not quick breaks. The PEM shows how long an impulse can echo, even after the initial push is gone. It also shows that biological communities do not simply snap back to an earlier state. Some species migrate, some adapt, and some disappear, leaving a reorganized baseline. What is known is robust across many sites and materials, which is why the PEM anchors arguments. The D13C drop appears in marine carbonates, organic matter, and soils, which reduces the chance it is a local quirk. Warming is supported by multiple temperature proxies, even with calibration debates and regional complications. The event is global, not a local oddity, and that globality is the core constraint. If the signal is everywhere, the cause must be large enough to touch everything. What remains unresolved is the source mix and the injection rate, because different sources can paint similar curves. Methane hydrates fit the light isotopic signature, but struggle with mass balance and sustaining the excursion at the required scale. Volcanism and thermogenic methane can supply carbon, especially during rifting and igneous intrusions, but must match timing and isotopes. Oxidation of soils and peat can contribute, yet requires a trigger and a pathway that mobilizes carbon quickly. The uncertainty is not ignorance, but a reminder that multiple mechanisms can cooperate. The PEM stays a warning benchmark because it shows rapid carbon release can reorganize Earth systems, even without humans. It also shows that the rock record can preserve a planetary shock as a simple curve, elegant and mute. That curve does not name its cause, and that is the problem we cannot escape. A line on a graph can be real, global, and still ambiguous about agency. This is where the Silurian hypothesis pays off, not as a claim, but as a limit on what we can know. Even if a pre-human industrial civilization existed, detection would be profoundly difficult, especially across tens of millions of years. Artifacts are local, fragile, and preferentially destroyed in the very places civilizations cluster, like coasts and river valleys. Ocean crust is recycled, coastlines migrate, and erosion edits the surface faster than we admit. Even continental interiors are not safe, because sediments are reworked and mountains rise and fall. Even global signals can be ambiguous because nature can mimic industry, and the proxies are not signed. A V13C excursion can come from methane, volcanism, or burning biomass, not only fossil fuels. Trace metals can spike from eruptions, hydrothermal pulses, or anoxia, not only smelting and manufacturing. Sedimentation changes can reflect climate and tectonics, not only land clearance and agriculture. The same data can support multiple stories, depending on the assumptions you bring. Synthetic markers sound decisive, Yet deep time is hostile to specificity and generous to confusion. Plastics fragment, oxidize, and may become carbon films that resemble natural organics, especially after burial and heating. PFAS-like compounds might not survive, or might be transformed into halogen signals with multiple sources. Exceptional preservation would require rare anoxic basins, rapid burial, and luck that survives later alteration. The archive is not a museum, and it does not curate what we wish it would keep, so the honest position is narrow and disciplined, and it resists the comfort of certainty. We cannot confirm a pre-human industrial civilization from the PTM alone, because the PTM is a signal without a signature. We also cannot claim that absence of artifacts disproves it, because the archive is a shredder with selective teeth. The hypothesis forces a methodological humility that is itself the point. It asks whether our confidence is evidence-based or simply habit. Then the final turn arrives, and it points forward instead of backward. The most haunting evidence is not what we might find in ancient rock. It is what future scientists will find in ours when our cities are gone and our languages are unspoken. They will not meet us, but they will meet our residues. We are writing a stratigraphic horizon with multiple independent signatures, and that redundancy is what makes it powerful. Atmospheric CO2 has risen at a rate visible in ice cores and now in sediments, and the pace itself becomes a clue. The D13C of atmospheric carbon is shifting negative through the Suez effect, as fossil carbon dilutes 13C with ancient light carbon. Ocean chemistry is changing as CO2 forms carbonic acid, and carbonate systems are responding in ways that echo older events. Even if the future forgets our names, the chemistry will remember our choices. We are leaving plastics and microplastics across oceans, soils and food webs, from abyssal mud to mountain snow. We are leaving radionuclides from nuclear testing as time-stamped fallout horizons, sharp enough to act like a global bookmark. We are doubling reactive nitrogen through fertilizers, shifting D15N patterns and driving eutrophication that turns bays into green, breathless water. We are moving metals, soot and persistent organics at global scale, and the distribution maps look like fingerprints. We're also leaving a biological signal that may be the clearest of all, because life records change in its own ledger. Biodiversity loss, invasive species mixing, and rapid range shifts are reorganizing ecosystems in decades, not millennia. Extinction rates and community turnover can become a biostratigraphic marker, visible as a sudden thinning of familiar forms. In the deep future, a sharp faunal break may read like a boundary, even if the story's forgotten. The question is whether the boundary will look accidental or intentional. This is why the Anthropocene debate matters, even if the label remains contested and politically charged. The question is whether these signals form a distinct mappable layer worldwide, rather than a patchwork of local disturbances. The deeper question is whether the layer will remain legible after diagenesis, burial and tectonic recycling. Future geologists will argue about our boundary the way we argue about theirs. They will have data, and they will have doubt. The mirror is uncomfortable because it collapses the distance between Petam and now, and it makes deep time feel close. Earth records rapid carbon release in a recognizable language, even when the speaker is unknown. A future core could show our D13C shift, warming pulse, and acidification trend stacked in the same column. It could be debated as volcanism, methane, or something else, if the context is lost. Our intentions may not fossilize, even if our emissions do. So the horror is not a hidden ancient they waiting to be unmasked in some romantic revelation. The horror is that we become chemistry, and chemistry becomes argument, and argument becomes footnotes. Our monuments may not survive, and our names may not survive, yet our perturbation will. The planet will keep the fingerprint and shred the biography. What will it feel like to be reduced to a curve? We can answer the central question only with disciplined ambiguity, because that is what the evidence permits. The PTM does not prove a pre-human industrial civilization, and it still has strong natural candidates that fit much of the data. Yet the Silurian hypothesis proves our methods have blind spots, because preservation is selective and attribution is hard. We can also prove that Earth will register our impact in the same proxy language we use to read the PTM. The tools we trust are the tools that will judge us. If something was here, the rock does not tell us who, it tells us what happens next. We began with a sealed deep-sea core, and learned to read it like evidence, not legend, through isotopes and redundant global signals. Across chapters, one lesson kept returning: Earth keeps records, not souvenirs, because tectonics, erosion, chemistry, and living burrowers shred the diaries of artifacts. So we widened the search from lost cities to planet-scale fingerprints, testing the Petm's carbon excursion, the Younger Dryas boundaries contested markers, and the human-scale anomalies of Göbekli Tepe, the Sphinx, and flood memory. The Silurian hypothesis did not promise an ancient empire, it exposed a blind spot, showing how a civilization could dissolve into chemistry, leaving only a statistical afterimage. At the same time, equifinality haunted every clue, because nature can mimic industry signatures, and proxies are powerful but unsigned. The Petm remains the case file that refuses to close, a rapid global negative D13C plunge paired with warming, acidification, and a slow recovery that models still struggle to reconcile. If it was methane hydrates, volcanism, baked sediments, or burning peatlands, the planet still recorded the event in the same language our era is writing. And if the Younger Dryas taught anything, it is that climate can flip within decades, while our archives argue over timing, contamination, and what counts as replication. Göbekli Tepe showed that complex coordination can appear before our neat narratives of farming and cities, and that disappearance can be deliberate, not accidental. The Sphinx reminded us how quickly official dates harden, even when geology, restoration and reuse can manufacture convincing illusions of certainty. Even the flood myths became a kind of noisy instrument, not a timestamp, but a reminder that human memory preserves patterns when stones do not. So the story resolves into a method, a humility, and a warning. Deep time is not empty, it is edited, and the edits are systematic. What then was that chemical scream 56 million years ago? Industry before humans, or a blind spot in how we interpret deep time? The honest answer is that the PTM is not a smoking gun, but it is a mirror, because the strongest surviving evidence would look like chemistry first and certainty last. If something was here before us, it may have vanished into the shredder, leaving only carbon's shadow and metals without a signature. But whether or not there was a prior civilization, the planet will keep ours, and future scientists may debate our layer the way we debate the Petm, arguing over sources, rates, and intent. Because in the end, Earth does not remember names, it remembers fluxes, and it files them in stone with a patience that outlives every monument. The most frightening possibility is not that we are first, or that we are second, it is that the record will be clear enough to convict and still too incomplete to forgive. Call to action. Keep asking what would count as uniquely industrial in deep time, support the slow work of cause and careful replication, and consider what signature we're choosing to leave behind. What then was that chemical scream 56 million years ago? Industry before humans, or a blind spot in how we interpret deep time? The honest answer is that the PTM is not a smoking gun, but it is a mirror, because the strongest surviving evidence would look like chemistry first and certainty last. If something was here before us, it may have vanished into the shredder, leaving only carbon's shadow and metals without a signature. But whether or not there was a prior civilization, the planet will keep ours, and future scientists may debate our layer the way we debate the Petm, arguing over sources, rates, and intent. Because in the end, Earth does not remember names, it remembers fluxes, and it files them in stone with a patience that outlives every monument. The most frightening possibility is not that we are first,